Thermodynamic laws in cosmic systems. From the earliest spark of creation to the cold stillness at the end of time, the universe is governed by laws not written in ink or stone, but etched into the very structure of reality. Among these, the thermodynamic laws stand as fundamental truths, rules that dictate how energy flows, how matter behaves, and how everything from a star's fiery heart to the quiet breath of a distant planet unfolds. The first law of thermodynamics, often simply called the law of energy conservation, states that energy cannot be created or destroyed, it can only change form. This simple truth is woven into the fabric of cosmic evolution. The intense radiation from the Big Bang, the energy released by nuclear fusion in stars, the silent pull of gravity, all of it abides by this principle. When a cloud of hydrogen collapses under gravity to ignite as a new star, the gravitational potential energy is not lost. It is transformed into thermal energy, igniting fusion and fueling light that travels across the cosmos for billions of years. But the conservation of energy alone cannot explain the direction of time or the nature of change. For that, we look to the second law of thermodynamics, a rule so fundamental that it defines the very arrow of time. It declares that in any closed system, the total entropy must increase or remain constant. In essence, energy will always tend towards spreading out, disorder will always increase, and heat will always flow from hot to cold. In a cosmic context, this law is omnipresent. From the expansion of the universe to the cooling of dying stars, from the chaotic turbulence inside stellar nurseries to the smooth uniformity of the cosmic microwave background, the second law quietly dictates the evolution of structure and the inevitable march toward equilibrium. Stars are born in defiance of entropy, gathering cold gas into hot, luminous spheres. Yet even they are temporary. As they radiate energy, they slowly fall into deeper entropic states. When a massive star dies in a brilliant supernova, its core collapses into a neutron star or black hole. While the explosion seems violent and chaotic, it actually releases a massive amount of energy into the surrounding space, increasing entropy on a grand scale. The compact remnant, now extremely ordered, is balanced by the chaos it leaves in its wake. The third law of thermodynamics states that as a system approaches absolute zero, its entropy approaches a minimum. In theory, a perfectly ordered state lies at the end of the thermodynamic road. But the universe resists this perfection. Absolute zero is unattainable in practice, and so the cosmos remains dynamic, alive with thermal fluctuations and complex patterns, even as it cools across billions of years. Still, the trajectory is clear. Every star that burns out, every gas cloud that disperses, every galactic collision that blends once distinct spiral arms, all contribute to the rising tide of entropy. But entropy does not mean simple decay. The fourth, less formal law, sometimes called the zeroth law, speaks of thermal equilibrium, stating that if two systems are each in equilibrium with a third, they are in equilibrium with each other. This principle underpins our understanding of temperature, balance, and the steady exchanges of heat and energy across the cosmic web. In the realm of stars, this plays out in the quiet balance between a star's inner fusion heat and the outward pressure of its radiating layers. When the fusion in the core ceases, balance is lost, and entropy resumes its climb. Thermodynamics is more than a framework, it is a lens through which the drama of the cosmos is revealed. From a single photon escaping a quasar to the simmering heat trapped in a planet's atmosphere, from the frozen deserts of Pluto to the incandescent plasma of stellar Carene. Thermodynamic laws govern the flow of energy, the emergence of structure, and the final surrender to chaos. Even black holes, the most mysterious and extreme objects in the known universe, follow these laws, storing entropy in their event horizons and radiating it away through Hawking radiation. Every galactic wind, every supernova remnant, every swirling accretion disk around a dying star is a testament to the relentless force of these laws. They do not just regulate the universe, they shape it, define it, and guide it. And in their quiet authority, they remind us that the universe is not random, but governed by deep universal patterns. Patterns born in the crucible of creation and destined to unfold until time itself runs cold. In this grand narrative, the thermodynamic laws are not abstract concepts. They are the heartbeat of the cosmos, the rhythm by which stars live and galaxies die. Entropy in expanding galaxies. As we step deeper into the mechanics of cosmic evolution, the thermodynamic laws we've just explored unfold their influence most elegantly in the story of galaxies. These sprawling cities of stars, gas, dust, and dark matter, each a gravitational symphony extending across tens or even hundreds of thousands of light years, are not static monuments. They are dynamic, ever-changing, and increasingly entropic structures, shaped profoundly by the expansion of the universe itself. When galaxies first began to form in the young cosmos, they emerged from density fluctuations in the nearly uniform sea of primordial hydrogen and helium. These faint ripples, seeded during cosmic inflation, grew over time under the gentle but persistent influence of gravity. Matter clumped together, collapsing into halos of dark matter, dragging ordinary matter along with it. This process, called gravitational collapse, was itself a counterpoint to entropy, briefly concentrating matter and energy into smaller, hotter, and more ordered configurations. But this increase in local order came at the cost of a broader increase in entropy, as gravitational potential energy was radiated away, often in the form of heat and high-energy photons. Once galaxies formed, they became crucibles of entropy's complex manifestations. The expansion of the universe, driven by dark energy, continues to stretch the very fabric of space-time. As this expansion accelerates, galaxies that are not gravitationally bound to one another drift further apart. This cosmological stretching has profound thermodynamic consequences. As space expands, the radiation within it becomes cooler and more dilute. Photons lose energy through redshift, their wavelengths lengthening as the cosmos inflates around them. This is not merely a loss of heat, it is an increase in disorder, a diffusion of energy that contributes to the ever-rising entropy of the universe. Within individual galaxies, entropy plays out in subtler yet equally profound ways. Star formation, once the dominant process in young galaxies, slows over cosmic time. The cool, dense clouds of molecular hydrogen necessary for stellar birth are gradually consumed or dispersed. Supernovae, stellar winds, and active galactic nuclei inject energy into the interstellar medium, heating it, stirring it, and making it less conducive to collapse. These feedback mechanisms distribute thermal and kinetic energy throughout a galaxy, increasing entropy while simultaneously halting further star formation. In this way, galaxies age. They become less structured, less active, more diffuse. Mature galaxies, especially ellipticals, formed through mergers and collisions, often appear smooth and spheroidal. This morphological transformation is another consequence of entropy. In the aftermath of galactic collisions, the once well-ordered orbits of stars are randomized. The gaseous components are shocked and heated, losing their ability to cool and collapse. The result is a structure that is more entropic, less defined, less dynamic, more uniform in temperature and composition. Over time, spiral arms fade, starburst activity dwindles, and galaxies settle into quieter, redder, more entropic states. The intergalactic medium, the vast, sparse gas that floats between galaxies, is also not immune. As galaxies shed heat and matter through outflows, jets, and radiation, this medium becomes a vast reservoir of entropy. Clusters of galaxies surrounded by enormous halos of hot, X-ray emitting gas represent some of the most entropic environments in the known universe. This gas, with temperatures of millions of degrees, is kept in place by the gravity of the cluster, but radiates energy slowly over time. Though hot, it is too diffused to form stars, and thus remains a dead end for structure, a symbol of entropy's slow conquest. Even the rotational dynamics of galaxies carry an imprint of thermodynamic history. The distribution of angular momentum, the interaction between dark matter halos and baryonic matter, and the drag imposed by interstellar gas all contribute to the complex evolution of galactic disks. Over time, these systems experience dynamical heating. Stellar orbits become more erratic, velocity dispersions increase, and the overall structure becomes more randomized, again signifying an increase in entropy. Yet this is not the end of the story. As entropy increases within galaxies, there remains a delicate and persistent balance, a thermodynamic tension between gravitational concentration and radiative diffusion. Gravity seeks to compress, to draw matter inward, to create order through collapse. But this order is always purchased at a cost, paid in radiation, heat, and disorder expelled to the broader universe. This tension defines the fate of galaxies. Whether they continue to form stars or fade into red embers, whether they merge and ignite or drift and die, their journeys are framed by entropy's slow crescendo. The expansion of galaxies is not just spatial, it is thermodynamic. It is the story of energy dispersing, of systems evolving toward uniformity, of structures slowly eroding under the subtle but relentless pressure of the second law. And yet, within this process lies beauty and motion. A reminder that even in decay, the universe remains alive with transformation. As we turn now toward the lives of stars, it becomes clear that this entropic narrative unfolds not just on galactic scales, but in the cores of suns themselves. The next step in our exploration brings us into the heart of equilibrium itself, where gravity and nuclear fire perform their ancient, delicate dance. Stellar equilibrium, the balance of fusion and gravity. Within the luminous engines scattered across the universe, those brilliant, blazing spheres we call stars, an extraordinary balance plays out. It is a cosmic tension between opposing forces, a negotiation between creation and collapse, a conversation held in nuclear tongues between the crushing grip of gravity and the fiery breath of fusion. This equilibrium, delicate yet enduring, lies at the heart of every star's existence. Without it, stars would not shine, galaxies would not form, and life itself would remain a whisper in the void. In the core of every main sequence star hydrogen atoms are forced so closely together by gravitational pressure that they overcome their mutual electrostatic repulsion. Under immense heat and density, these atoms fuse to form helium, releasing prodigious amounts of energy in the process. This energy, born from the very fabric of atomic nuclei, radiates outward as photons and thermal pressure. That pressure pushes against the inward pull of gravity, establishing a balance, a state of stellar equilibrium. It is this equilibrium that grants stars their seemingly eternal glow. Yet this balance is not static. It is dynamic and constantly self-regulating. If gravity gains an advantage and compresses the star more tightly, fusion rates increase, producing more energy and pushing back with greater force. If fusion overpowers gravity, the star expands slightly, cooling and slowing the reaction rates, allowing gravity to reassert control. This intricate feedback loop enables stars to remain stable for millions to billions of years, quietly forging the elements of life within their cores. This stellar equilibrium is most pronounced in stars like our Sun, moderate in size and age, fueled by the proton-proton chain reaction in their cores. But larger stars follow a different path, burning hotter and faster through the CNO cycle, which fuses hydrogen into helium using carbon, nitrogen, and oxygen as catalysts. These massive stars exist in a more volatile equilibrium, where even the slightest imbalance can trigger catastrophic outcome. The historical understanding of this balance emerged gradually through the 20th century. Before the mechanisms of nuclear fusion were known, scientists like Arthur Eddington hypothesized that something in the stellar core must resist gravitational collapse. It wasn't until the works of Hans Bethe and others during the mid-century that nuclear reactions were confirmed as the source of stellar energy. The discovery reshaped our understanding of stars, not as eternal beacons, but as finite reactors governed by physical laws. As hydrogen is consumed and helium accumulates in the core, the equilibrium begins to falter. Gravity, no longer sufficiently opposed, compresses the core further, increasing its temperature. New fusion reactions ignite helium into carbon, then carbon into heavier elements like oxygen, neon, silicon, and eventually iron. Each stage represents a new temporary equilibrium, but this stage represents a new temporary equilibrium. But this stage represents a new temporary equilibrium. But this stage represents a new temporary equilibrium. Iron marks the limit. It cannot yield energy through fusion. When a massive star's core becomes iron-rich, fusion halts. Gravity, unchecked at last, wins. The core collapses in mere seconds, triggering a core bounce and then a supernova, one of the most violent events in the cosmos. The outer layers are hurled into space, seeding the galaxy with elements forged in the dying star's furnace. What remains is either a neutron star, where quantum degeneracy pressure holds collapse at bay, or a black hole, where gravity has no rival and equilibrium has lost its war. Smaller stars follow gentler paths. A star like our Sun will expand into a red giant as helium burning begins in the core and hydrogen fusion continues in a surrounding shell. In time, its outer layers will drift away, forming a planetary nebula, while the core contracts into a white dwarf. Here too, a new form of equilibrium arises, not from fusion, but from the pressure of electrons resisting further compression. Though it no longer shines with the vigor of youth, the white dwarf represents a final resting state, a balance once again forged in opposition to collapse. Across the universe, stellar equilibrium is not merely a matter of physics, It is the architecture of time and complexity. It is through this fragile standoff that stars live long enough to create the elements of carbon, oxygen, nitrogen, the ingredients of biology. It is through this balance that planets form in the calm after stellar birth, that moons gather, that atmospheres arise. Life depends not only on the stars, but on the precise harmony within them. This equilibrium also teaches us about entropy in a new context. Though stars resist entropy locally, they do so only by accelerating it universally. Every photon they emit is a step toward thermal diffusion. Every reaction in their core increases the total entropy of the cosmos. Stellar equilibrium, therefore, is not the opposite of entropy. It is the means by which entropy proceeds, regulated and staged through structured resistance. As we move forward, the story of entropy becomes even more extreme, confronting regions where gravity reigns supreme and order is swallowed whole. The next chapter unfolds at the very edges of physics, in the event horizons of black holes, where equilibrium ceases and entropy reaches its cosmic maximum. Black holes and maximum entropy. A journey through stellar equilibrium inevitably leads us into the darkest and most mysterious corners of the universe. Places where equilibrium shatters, where the known laws of physics bend, and where entropy reaches its absolute peak. Black holes, those gravitational abysses born from the catastrophic death of massive stars, are not merely the graveyards of matter. They are the ultimate thermodynamic endpoints. In these regions of extreme density and warp space-time, entropy finds its fullest expression not in chaos, but in silence. When a massive star exhausts its nuclear fuel, fusion can no longer counteract gravity's relentless inward pull. The core collapses with such intensity that even the quantum pressures resisting further compression are overwhelmed. No known force can halt the implosion. What remains is a singularity, an infinitely dense point hidden behind a boundary called the event horizon. This horizon marks the edge beyond which nothing, not even light, can escape. From an external perspective, the black hole becomes a featureless, opaque sphere, a region defined not by its contents, but by its mass, spin, and electric charge. At first glance, this might appear to violate everything we understand about entropy. The collapse of a star into a simple, silent object seems to reduce complexity. Where once there were layers of plasma, nuclear reactions, magnetic fields, and convective flows, there now exists only a black void. How could this represent maximum entropy? The answer lies in a radical shift in perspective, one that emerged from the groundbreaking work of physicists like Stephen Hawking, Jacob Bekenstein, and others during the late 20th century. Bekenstein proposed a revolutionary idea that black holes possess entropy proportional not to their volume, but to the surface area of their event horizon. This suggestion defied intuition. In classical thermodynamics, entropy typically scales with the amount of matter or energy inside a system. But in a black hole, information about the matter that falls in seems to vanish from view. If entropy is a measure of the number of microstates, ways a system can be arranged, then the black hole, hiding all internal distinctions behind a smooth horizon, seemed to challenge the very meaning of entropy. Hawking expanded this insight by applying quantum field theory to the curved space-time near a black hole. In a brilliant synthesis of quantum mechanics, thermodynamics, and general relativity, he showed that black holes are not entirely black. They emit radiation due to quantum fluctuations near the event horizon, a phenomenon now known as Hawking radiation. This radiation has a temperature, and therefore, by definition, the black hole must have entropy. The entropy, Hawking found, is astonishingly large, far greater than that of any other object of similar mass. And it scales precisely with the surface area of the event horizon, measured in Planck units. This realization transformed our understanding. Black holes are not exceptions to the laws of thermodynamics. They are their fullest expression. In fact, a black hole contains the maximum possible entropy that can be packed into a given region of space. No other configuration of matter can surpass it. This is a profound statement about the limits of information, structure, and the fabric of reality itself. Consider a massive cloud of gas collapsing under gravity. As it contracts, it heats up and radiates energy, shedding entropy into the surrounding space. Eventually it may become a star or perhaps a supernova. But if its mass is great enough and all resistance fails, it becomes a black hole. In this final transformation, the internal complexity of the system vanishes from external view, but the entropy increases drastically. The black hole, in a sense, records only the external characteristics, mass, charge, spin, while all other information becomes inaccessible. This leads to one of the most profound puzzles in modern physics, the black hole information paradox. If information cannot be destroyed, where does it go when it crosses the event horizon? Efforts to resolve this paradox have led to deep insights in quantum gravity, string theory, and holography. One of the most promising ideas is the holographic principle, which suggests that all the information contained in a volume of space can be described by a theory defined on its boundary. In other words, the universe itself might be like a hologram, where reality is encoded not within, but on the surface. Black holes, with their entropy proportional to surface area, are the clearest expressions of this concept. In this thermodynamic view, black holes are not anomalies. They are thermodynamic machines, converting mass into gravitational curvature and radiative heat. Over unimaginably long timescales, they evaporate through Hawking radiation, slowly shrinking until they vanish. This final act, when the black hole radiates its last quantum of energy, raises fundamental questions. Does the entropy disappear with it, or is the information somehow preserved in the radiation? These are questions not yet answered, but their pursuit has opened entirely new vistas in theoretical physics. Yet the implications of black hole entropy are not confined to theoretical puzzles. They affect how we understand the universe as a whole. In a universe filled with stars and galaxies, entropy is vast but still finite. As matter collapses into black holes over cosmic time, more and more entropy becomes concentrated behind event horizons. Black holes, scattered across galactic centers and cosmic voids, become entropy reservoirs, silent, invisible markers of cosmic time in progression. In this way, they help drive the cosmos toward its ultimate fate. And that fate, as we shall see, is one of growing stillness. As the universe expands, cools, and empties, entropy does not decline, it accelerates. The cosmic background radiation fades, stars burn out, galaxies drift into isolation, and black holes eventually evaporate. The future of the universe is not one of fire, but of cold, quiet equilibrium. To understand that haunting trajectory, we must now turn to the lingering afterglow of the Big Bang itself, the most ancient thermal signal in existence, frozen in time and stretched across the sky. The cosmic microwave background, a snapshot of equilibrium. Amid the grand narrative of entropy's ascent and the march toward cosmic stillness, there remains a relic, a whisper from the infancy of everything, preserved in the silence between stars. It is not a remnant of matter, nor a shadow of structure, but a bath of ancient light. The cosmic microwave background, this pervasive radiation, stretched thin by eons of expansion, is more than a passive echo of the Big Bang. It is the oldest image of the universe we possess, a thermal snapshot of equilibrium that reveals the precise moment when order first yielded to structure, when energy and matter decoupled and the cosmos began to breathe freely. To truly understand the cosmic microwave background, one must journey back to a time when the universe was unimaginably young, less than 400,000 years after the Big Bang. At that point, it was a seething, opaque plasma of electrons, protons, and photons. Light could not travel freely, constantly scattered by charged particles in an endless fog. But this fog was not chaotic. It was in thermal equilibrium, an almost perfect balance of radiation and matter. The entire universe was essentially a single thermodynamic system, hot and dense, uniform across vast stretches of space. As the universe expanded, it cooled. This cooling was not uniform, but it followed precise thermodynamic rules. Once the temperature fell below a critical threshold, electrons and protons could finally combine into neutral hydrogen atoms. This event, known as recombination, transformed the universe. Photons, no longer trapped by charged particles, were released to stream freely through space. This was the moment of decoupling, when light and matter parted ways. The radiation released in that instant has continued its journey ever since, red-shifted by cosmic expansion into the microwave portion of the electromagnetic spectrum. Discovered in the mid-20th century by accident, by Arno Penzias and Robert Wilson, while calibrating a radio antenna, the cosmic microwave background was initially perceived as a puzzling hiss of noise, uniform in every direction. But its discovery confirmed a major prediction of the Big Bang theory and revolutionized cosmology. What Penzias and Wilson heard was not static. It was the first detectable thermal glow of the universe itself, stretched across the sky, a nearly perfect blackbody spectrum at just under 3 degrees above absolute zero. Subsequent measurements have refined our understanding with astonishing precision. Satellites like COBE, WMAP and Planck have mapped the cosmic microwave background in exquisite detail. They reveal that this background is not entirely uniform. Tiny fluctuations, variations in temperature on the scale of millionths of a degree, dot the sky. These fluctuations are not noise. They are the fingerprints of quantum fluctuations magnified by inflation and frozen into the fabric of space. They represent regions where matter was slightly denser or slightly less dense, seeds from which galaxies, stars, and planets would eventually form. These temperature variations are a delicate balance between competing forces, gravity pulling matter inward and radiation pressure pushing outward. This tug-of-war, known as acoustic oscillation, produced a pattern of ripples in the plasma of the early universe. The sound of creation itself, vibrations in the primordial soup, left an imprint in the sky that remains today. The spectrum of these fluctuations, the angular scales of their distribution, the polarization of the light, each carries detailed information about the universe's composition. its age, its curvature, and its destiny. The cosmic microwave background is, in essence, a map of thermodynamic equilibrium, disturbed ever so slightly. It is the line between chaos and order, between radiation and matter, between the opaque early universe and the transparent cosmos that followed. It is not only a record of the universe's birth, it is also a guidebook for its future. From the precision of its measurements, we know the universe is flat to within a small margin. We know the exact proportion of ordinary matter, and dark energy. We know that the universe is expanding not just steadily, but accelerating. Even the minute anisotropies in the background help illuminate the fate of entropy. They tell us how structure arose, how galaxies formed, and how energy was distributed. They reflect a cosmos that began in high uniformity, but inevitably diverged toward complexity, chaos, and increasing disorder. The smoothness of the background confirms that initially entropy was low, extraordinarily low. It was this low entropy beginning that allowed for the arrow of time, for thermodynamic progression, and for the formation of all that followed. The cosmic microwave background, therefore, is not simply light, it is memory. It is equilibrium captured in its final moment before fragmentation, equilibrium suspended in a sea of cosmic variance. It reminds us that entropy did not begin as disorder, but as potential. The potential to break symmetry, to create contrast, to form complexity. From its quiet glow, we learn how entropy drives structure, how energy flows from uniformity into form, and how the cosmos became diverse in temperature, density, and identity. And as this light continues its journey through an ever-expanding space, it cools further. The once blinding brightness of the early universe is now a cold whisper, and it will fade even more in the ages to come. Yet this fading too is entropy at work, the universe settling into equilibrium on the grandest scale. But equilibrium is not always global. In pockets across the cosmos, planets hold atmospheres, and atmospheres hold heat. The interplay of energy between starlight, planetary rotation, magnetic fields, and chemical composition reveals another layer in the thermodynamic story, an exploration into planetary atmospheres and the fragile balance they maintain with the space around them. Heat death of the universe, ultimate entropy. From the spark of creation to the cooling embers of cosmic evolution, the universe has been a stage for entropy's relentless performance. Each fluctuation in the cosmic microwave background, every star that ignited, every black hole that formed, all are verses in a thermodynamic symphony building toward a final movement that awaits in the farthest reaches of time. That final movement has a name: the heat death of the universe. It is not an explosion, nor a collapse. It is a fading, a settling into perfect stillness, where entropy reaches its absolute maximum and all processes as we know them cease. To grasp this fate, one must first understand entropy not as destruction, but as the spread of usable energy. Every star that burns transfers energy from concentrated nuclear fuel into diffuse heat and light. Every galaxy that merges, every gas cloud that cools, every gravitational collapse that ends in a black hole, all transfer energy from one form to another. But in each transfer, a portion becomes unavailable for work. It radiates into space, scattering thinly across an ever-expanding cosmos. Entropy is not chaos in the colloquial sense, It is the tendency of energy to equilibrate, to spread out evenly until no gradients remain. No hot and cold, no dense and diffuse, no potential left to act upon. This thermodynamic unfolding does not happen all at once. It unfolds over unimaginable spans of time, far beyond the age of stars, beyond the death of galaxies, into an epoch dominated not by matter and light, but by black holes, radiation and vacuum. The so-called stelliferous era, the age of stars, is already in decline. Star formation has slowed, and in time galaxies will exhaust their reserves of cold gas. New stars will no longer be diluted as the fabric of space stretches. These photons reshift, losing energy, contributing less and less to the temperature differences needed to drive chemical, mechanical, or biological processes. Planets freeze, atmospheres dissipate, black dwarfs, neutron stars, and stellar remnants populate a cold, dark sky. Over far greater timescales, the gravitational dance continues. Some of these remnants may collide, forming new bodies, briefly warmed by kinetic energy. But these will be rare. Most stellar remnants will drift into interstellar exile. Eventually, gravitational interactions eject many objects from their host galaxies, sending them into the void between galaxy clusters. The cosmos becomes sparse and dark, but entropy has not yet reached its crescendo. Black holes still lurk, massive, silent, and dominant. Over eons, they absorb matter and radiation, growing in mass and influence, yet even they are not eternal. Through Hawking radiation, black holes gradually lose mass, emitting faint thermal radiation as quantum effects bleed energy from their horizons. The larger the black hole, the slower this process. It takes longer than the current age of the universe multiplied by numbers that defy imagination. But the process is certain. One by one, black holes evaporate, shrinking until nothing remains. With their demise, even the most extreme concentrations of energy surrender to entropy. At this point, the universe enters what physicists call the dark era. No stars, no galaxies, no black holes, just a thin, cold soup of elementary particles. Photons, neutrinos, electrons, and positrons spreading across space that continues to expand. The temperature of the universe asymptotically approaches absolute zero, yet never truly reaches it. There are no energy differences left to exploit, no complex structures to maintain, no gradients to drive reactions. It is a state of thermodynamic equilibrium so perfect that nothing can change, because change itself requires imbalance. This is the heat death. Not fire, not frost, but stillness. The total entropy of the universe is at its maximum, and with it comes the cessation of all activity. All clocks stop, not because they break, but because there is no longer anything to measure. All movement halts, not because of resistance, but because there is nowhere left to go. Time loses its meaning when nothing changes from moment to moment. Time loses its meaning when nothing changes from moment to moment. The idea of heat death was first proposed in the 19th century by physicists like Lord Kelvin and Rudolf Clausius, pioneers of thermodynamics. They recognized that the second law demanded a final state, one where entropy could increase no further. What they did not have then, but what modern cosmology now provides, is a clear understanding of how this state would come about on cosmic scales. Today, supported by observations of cosmic expansion, thermodynamic measurements, and quantum theory, heat death is considered the most likely long-term fate of our universe. Yet, this ultimate entropy also serves as a profound philosophical mirror. It invites reflection not just on the fate of stars and galaxies, but on meaning, time, and existence. Why did the universe begin in such a low entropy state, allowing time and life to unfold? What does it mean that all complexity, all structure, all memory and thought are brief fluctuations against a background that will end in total equilibrium? These are questions that blend physics with metaphysics, cosmology with consciousness. Still, the journey toward heat death is not a surrender, it is a revelation. It tells us that the cosmos, though vast and cold, is governed by laws of astonishing precision. It reminds us that energy has a destiny, that complexity has a cost, and that time itself is shaped by thermodynamic gradients. And even as the universe drifts into silence, the echoes of its fiery birth remain encoded in light, matter, and memory. But not all equilibrium is cosmic. In pockets across space where starlight meets the chill of shadow, planets form atmospheres. Delicate envelopes of gases that trap heat, circulate energy, and defy the cold void beyond. The next chapter in this unfolding story draws us toward these local balances, toward planetary atmospheres, and the fragile thermal harmony that sustains them. Planetary atmospheres and thermal balance. In a universe tending inexorably toward uniformity, where galaxies drift apart and stars flicker out, it is within the slender, fragile veils of planetary atmospheres that equilibrium finds one of its most dynamic expressions. Unlike the vast entropy of black holes or the icy quietude of the cosmic future, planetary atmospheres are systems of balance in tension. Ever shifting, constantly adjusting, shaped by sunlight, gravity, chemistry, and rotation, these atmospheric envelopes are not static. They breathe, circulate, and pulse with the rhythms of thermodynamic exchange. A planetary atmosphere exists only when gravity can retain gases around a planetary body and when those gases do not escape into space. But its function goes far beyond retention. Atmospheres act as mediators between the searing heat of a star and the cold vacuum of space. They trap energy, distribute it, and in many cases moderate a planet's surface conditions to allow for the stability of liquids, the formation of weather systems, and, under rare circumstances, the emergence of life. This regulation is a form of thermal equilibrium. Not the final, absolute stillness seen in cosmic heat death, but a dynamic, delicate balance between energy input and energy loss. The source of this input is primarily stellar radiation. When sunlight strikes a planet, some is reflected back into space, while the rest is absorbed by the surface or atmosphere. This absorbed energy is re-emitted as infrared radiation, longer wavelength light that carries heat away. But certain atmospheric gases, particularly carbon dioxide, methane, and water vapor, absorb this outgoing radiation and re-radiate it in all directions, including back toward the surface. This greenhouse effect is not a flaw, it is essential. Without it, Earth's average temperature would be far below the freezing point of water. It is the modulation of this process that defines a planet's climate and thermal balance. The balance is further complicated by atmospheric composition, pressure, albedo, and cloud dynamics. On Venus, a thick carbon dioxide-rich atmosphere traps so much heat that surface temperatures soar beyond what would be expected simply from its distance to the Sun. Its clouds reflect much of the sunlight that reaches it, yet its surface remains hotter than a furnace due to the intense greenhouse effect. Mars, by contrast, has a thin atmosphere with little ability to trap heat, leading to enormous temperature swings between day and night. Both planets illustrate the sensitivity of thermal equilibrium to atmospheric characteristics. Earth occupies a rare position, what is often called the habitable zone, where temperatures permit liquid water to exist stably. But what truly enables Earth to sustain life is not just its distance from the Sun, but its atmospheric regulation. Our planet's atmosphere has evolved alongside its geology and biology. Oxygen, a byproduct of photosynthesis, reshaped the chemistry of the air. Water vapor participates in a self-reinforcing feedback loop, with clouds both reflecting sunlight and trapping heat. Aerosols, both natural and human-made, influence the energy budget by scattering radiation or serving as nuclei for cloud formation. Thermal balance is maintained through an intricate energy budget. Energy in equals energy out, on average. When this balance is perturbed, the climate shifts. Ice ages, warm periods, and sudden climatic events all result from imbalances caused by orbital variations, volcanic eruptions, solar activity, or anthropogenic influence. In modern times, the addition of greenhouse gases from human industry has tipped this balance. More heat is retained than radiated away, leading to global warming, melting ice, rising seas, and altered weather patterns. The planet is not drifting into a new equilibrium. It is undergoing a rapid thermodynamic transition, one that challenges its capacity for regulation. But Earth is not alone. Across the solar system, planetary atmospheres reveal the diversity of thermal regulation. Titan, Saturn's largest moon, has a dense, nitrogen-rich atmosphere with methane clouds and liquid methane lakes. Its surface is bitterly cold, yet its thick haze performs a kind of insulation. Jupiter and Saturn exhibit banded atmospheric flows, driven by internal heat and fast rotation, resulting in vast storm systems that persist for centuries. Uranus and Neptune, cold giants far from the Sun, release more heat than they receive due to ancient formation energy still trapped within. Even planets without atmospheres engage in thermal balancing acts. Mercury, lacking any significant gaseous envelope, undergoes the most extreme temperature variations in the solar system. The Moon, similarly barren, alternates between scorching sunlight and frigid shadow. These examples underscore the importance of atmosphere in buffering and redistributing energy. In the grand scheme, planetary atmospheres represent a local rebellion against entropy's broader trajectory. They maintain pockets of structured energy flow, sustaining gradients and cycling materials. They are systems in flux, resisting immediate equilibrium, preserving complexity. Yet even here, entropy advances. Atmospheric molecules are lost to space through escape velocity or photodissociation. Weather erodes surfaces, clouds dissipate, and gases slowly leak into the void. Over deep time, unless replenished, atmospheres thin, thermal balance fails, and planets cool to match the temperature of the cosmic background. The study of planetary atmospheres is more than a catalogue of climates. It is an exploration into how thermodynamics creates and limits conditions for life, structure, and persistence. It shows how, even in isolation, a planet's dance with its star can sustain temporary order amid universal entropy. Yet atmospheres are only one part of the story. Beneath them, in the solid and liquid layers of a world, another kind of equilibrium plays out: chemical equilibrium. As we continue this journey through cosmic thermodynamics, the next step takes us to alien worlds. As planetary atmospheres swirl with storms, gases, and radiation, an equally profound story unfolds beneath the clouds, within the very soils, oceans, and mineral layers of planets and moons scattered across the cosmos. This is the domain of chemical equilibrium, a delicate thermodynamic balance where atoms and molecules interact, react, stabilize, and evolve. While thermal balance governs the exchange of energy between a planet and its star, chemical equilibrium governs the transformation of matter within and upon the surface. And when observed on alien worlds, far removed from the familiar chemistry of Earth, these equilibria reveal how entropy sculpts the very essence of alien landscapes and, possibly, the conditions for life itself. At its core, chemical equilibrium is the state in which forward and reverse chemical reactions occur at equal rates. It does not imply stasis, but dynamic balance. A molecular conversation that continues indefinitely, with no net change in composition. Reactions move toward equilibrium not because they are directed, but because of statistical inevitability, the tendency of systems to reach a state of minimum free energy. This tendency is thermodynamic entropy, expressed on a molecular scale, driving mixtures to balance, compounds to stabilize, and phases to distribute. On Earth, chemical equilibrium governs everything, from ocean pH and weathering of rocks to metabolic pathways and atmospheric composition. But on alien worlds, removed from Earth's biosphere and geosphere, chemical equilibrium plays out under vastly different pressures, temperatures, solvents, and elemental abundances. Each of these factors shapes the direction and behavior of chemical reactions, giving rise to environments that challenge our understanding of what is stable, what is reactive, and what is possible. Take, for instance, the subsurface ocean of Europa, one of Jupiter's icy moons. Beneath its frozen crust lies a global ocean kept liquid by tidal heating. In this dark, pressurized sea, water interacts with a rocky sea floor, possibly undergoing serpentinization, a chemical process in which ultramafic rock reacts with water to produce hydrogen gas. This hydrogen, in turn, could react with carbon dioxide or sulfate, creating chemical gradients that mimic the conditions of Earth's hydrothermal vents. In such environments, equilibrium is never static. It is the constant striving of molecules to balance energy across interfaces of rock, water, and potential biochemistry. On Titan, Saturn's largest moon, chemical equilibrium manifests in an alien medium. Its thick atmosphere, composed primarily of nitrogen with a significant proportion of methane, allows for a methane cycle akin to Earth's hydrological cycle. Methane rains, flows into lakes, and evaporates into clouds. But beyond this dynamic, Titan's surface chemistry reflects slow photochemical reactions driven by sunlight and cosmic rays. Hydrocarbons and nitriles form complex organic molecules, tholins, that accumulate as the reddish haze. These compounds exist in a fragile equilibrium, continuously reshaped by incoming energy and atmospheric conditions. Their stability and transformation are windows into prebiotic chemistry, giving us a glimpse into the kinds of chemical systems that might precede life. Mars offers another variation. Its thin atmosphere and cold, oxidizing surface drive a chemical equilibrium dominated by perchlorates, sulfates, and iron oxides. These compounds are not randomly distributed. They represent the end point of prolonged exposure to ultraviolet radiation, dry winds, and ancient water flows. The Martian regolith, with its rusty hue, is the record of a planet's attempt to reach chemical stasis under evolving environmental pressures. Even its now silent riverbeds and deltas hold clues to past aqueous equilibria, where salts precipitated, acids formed, and minerals locked in memories of a wetter, more reactive past. On Venus, the surface chemistry is shaped by extremes: temperatures hot enough to melt lead, and a carbon dioxide-rich atmosphere dense with sulfuric acid. The rocks on Venus undergo chemical weathering not through water, but through interaction with corrosive gases. This leads to an equilibrium dominated by carbonates, sulfides, and oxides, maintained under crushing pressure and suffocating heat. It is a brutal, relentless, thermodynamic push toward chemical finality, one that highlights the diversity of equilibrium states made possible by planetary conditions. Beyond the solar system, exoplanets expand this diversity exponentially. Some orbit close to their stars, with daysides hot enough to vaporize rock and nightsides cold enough to freeze gases. In such environments, equilibrium is not global but regional. Silicate vapors may condense into clouds of molten minerals. Exotic compounds like titanium oxide or vanadium dioxide could dominate atmospheric spectra. On water-rich super-Earths, deep oceans under high pressure might create supercritical water, altering the thermodynamic behavior of solutes and minerals. In carbon-rich environments, planets could exhibit equilibria centered on carbides, graphite, or even diamond. A mineral stable not only under pressure, but potentially across entire crusts. Chemical equilibrium is also intimately tied to disequilibrium, an essential concept when considering the possibility of life. On Earth, life thrives by exploiting chemical gradients, maintaining disequilibrium through metabolic processes. Wherever we find persistent chemical imbalances, such as methane and oxygen coexisting in an atmosphere, or reduced and oxidized compounds side by side, we find the potential for biological processes. So, alien worlds exhibiting these features, particularly in the presence of liquid solvents and complex chemistry, become candidates for further scrutiny. The search for biosignatures in exoplanetary atmospheres, conducted through spectroscopic analysis, often focuses on such thermodynamic irregularities, signals that something is holding equilibrium at bay. This idea underscores a profound truth. Equilibrium defines the baseline, but it is in resisting that baseline, maintaining imbalances, that complexity and life emerge. Entropy drives systems toward balance, yet in the process opens pathways for transient order. Chemical equilibrium is not the end of chemistry, but the stage on which entropy, structure, and possibility perform. As we move forward, our journey turns once again to entropy's most persistent marker, the direction of time. For all these processes, from planetary weather to molecular transformations, unfold along a one-way street, the arrow of time. It is not merely a function of clocks, but a thermodynamic truth, defined by entropy and visible in every chemical trace, every planetary surface, and every dying star. Entropy and the arrow of time. All throughout the cosmos, from the fading light of the cosmic microwave background to the chemical equilibrium on alien landscapes, one principle guides the unfolding of events with unwavering consistency. Time moves forward. Stars form, burn, and die. planets cool, black holes evaporate, molecules react and settle, memory accumulates while the future remains uncertain. This directional flow of time, from past to future, is so deeply embedded in human experience that we seldom question it. Yet, at the heart of physics, time itself appears symmetrical. The laws that govern motion, gravity, and quantum fields do not prefer one direction over another. What then gives time its arrow? The answer lies in entropy. Entropy, as defined in thermodynamics, is a measure of disorder, or more precisely, the number of possible microstates a system can assume while maintaining the same macroscopic conditions. In essence, it is a count of how many ways a system can be arranged without changing what we observe on the surface. Systems naturally evolve toward configurations with higher entropy because there are simply more of them. A broken glass on the floor has more possible disordered arrangements than an intact one on a shelf. The same principle applies to clouds of gas, biological systems, or even galaxies. Time appears to move forward because systems evolve from less probable, lower entropy states to more probable, higher entropy states. This tendency, this irreversible progression, is what defines the arrow of time. Unlike position or velocity, which can be reversed in equations without contradiction, entropy cannot decrease on its own. It is a statistical law, not a deterministic one, and yet it is unbreakable in practice. The universe expands, structures break down, and complexity arises, not in defiance of entropy, but as part of its deep and subtle narrative. The arrow of time becomes most visible when systems move away from equilibrium. Consider a cup of hot coffee cooling in a room. The coffee's heat dissipates into the surrounding air until both reach thermal equilibrium. The process is irreversible. One never sees heat spontaneously flow from a cooler room into a hotter cup. The laws of motion would allow it, but entropy forbids it on statistical grounds. The initial state, with all thermal energy concentrated in one place, is highly ordered and improbable. The final state, in which energy is evenly distributed, is far more likely. Thus, the progression from hot to cold is not driven by time itself, but by entropy's directive. On cosmic scales, the arrow of time manifests in the growth of structure. In the earliest observable universe, as revealed by the cosmic microwave background, matter and radiation were almost perfectly uniform. This low entropy state is paradoxical. Why would the universe begin in such an improbable condition? No known physical law demands it. Yet from this smooth beginning, tiny fluctuations grew under the influence of gravity, creating galaxies, stars, planets, and all subsequent complexity. The direction of time aligns with this increase in entropy. From an ordered origin to a future of diffused energy and thermodynamic silence. In biology, time's arrow is equally clear. Life depends on energy flows and chemical reactions that proceed in a consistent direction. Organisms metabolize nutrients, replicate cells, form memories, and age. These processes consume usable energy and increase the entropy of the surrounding environment. The living system itself may maintain or reduce its internal entropy temporarily, but only by exporting disorder outward. This thermodynamic transaction gives rise to the perception of progress, decay, and irreversible change. Memory, experience, and history all depend on this asymmetry. A world in which entropy decreased would not only be physically alien, it would erase causality and render cognition itself impossible. In information theory, entropy also defines the direction of data. Messages become degraded over noisy channels, images blur, files corrupt. These processes mirror thermodynamic entropy. The loss of distinction between signal and noise is a form of temporal progression. Once clarity dissolves into randomness, it cannot be reversed without external input. Thus, the arrow of time governs not just the physical world, but the conceptual one. Our records, languages, and technologies. Yet, the mystery deepens when we confront the fundamental laws of physics. The equations of motion, whether Newtonian, relativistic, or quantum, do not distinguish past from future. Time reversal symmetry is a built-in feature of most physical systems. If one were to film an orbit or an electron in motion and then play it backward, the equations would still hold. This symmetry implies that the arrow of time is not intrinsic to the laws themselves, but emerges from the boundary conditions of the universe. This brings us to a profound question. Why did the universe begin in a state of low entropy? What set the initial conditions that allowed time to have a direction at all? Some physicists suggest that this asymmetry is rooted in the very structure of space-time at the Big Bang. Others propose that time's arrow could be local, that the direction of entropy increase might reverse in other parts of a larger multiverse. These ideas remain speculative, but they underscore how deeply entropy is woven into the mystery of existence itself. On a more concrete level, the arrow of time provides a unifying thread through every scientific discipline. It links cosmology with chemistry, biology with geology, memory with mechanics. It gives structure to narratives and meaning to experience. It explains why we can remember the past but not the future, why cause precedes effect, and why death follows birth. In the final analysis, entropy is not merely a description of disorder, it is the architect of time. It builds direction where symmetry reigns, it gives shape to change. And while the heat death of the universe marks the endpoint of entropy's rise, the arrow of time will not vanish. It will simply reach its terminal point, a cosmic stillness where nothing moves because nothing can. Yet entropy's path is not always straightforward. It curves through gravity, pools in star clusters, flows through collapsing clouds of gas and dust. The arrow of time interacts with gravitational collapse in ways that bend, focus, and intensify disorder into extraordinary structures. In the next chapter, we turn toward these dense stellar environments, exploring how gravitational collapse fuels the entropic flow and reveals new dimensions in the thermodynamic saga of the universe. Gravitational collapse and entropic flow. Throughout the cosmic narrative, entropy flows like an unseen river, always advancing, never reversing, guiding time, shaping stars, and setting the stage for life and death. But while entropy often conjures images of disarray and heat loss, the role it plays in gravitational collapse reveals a more nuanced and paradoxical story. Here, disorder births structure. Chaos sculpts form. In these rare and remarkable phenomena, the very force that tears down also builds up. Gravitational collapse does not oppose entropy, it channels it, guiding energy from uniformity into concentrated complexity. It is in this transformation that we find one of the most compelling intersections of thermodynamics and cosmic architecture. Gravitational collapse begins with a deceptively simple premise. Regions of matter that become slightly denser than their surroundings will, under the influence of their own gravity, begin to pull in more material. As this mass increases, so does gravitational attraction, accelerating the inward motion. This runaway process causes gas clouds, primarily composed of hydrogen and helium, to condense into tighter configurations. Over time, this compression leads to the formation of stars, stellar clusters, galaxies, and black holes, the pillars of cosmic structure. Yet in terms of entropy, this apparent movement from spread-out gas to localized mass seems to contradict the second law of thermodynamics. How can concentrated order emerge from a universe governed by disorder? The resolution lies in understanding the peculiar thermodynamic behavior of gravitational systems. Unlike conventional thermodynamic systems where energy spreads out to reach equilibrium, gravitational systems increase their entropy by becoming more clumped, not less. This counterintuitive principle was first explored through studies of star clusters and galaxies. In a gas cloud, when particles move closer together under gravity, their potential energy decreases. But this loss must be compensated by an increase in kinetic energy, meaning the system heats up. The sensor becomes hotter and denser while the outer regions expand and cool. This redistribution increases the number of possible microstates for the entire system, thereby raising its entropy. As the collapse deepens, complexity emerges. In stellar nurseries, the dense cores of molecular clouds become the seeds for protostars. As material falls inward, it releases gravitational potential energy, heating the core until nuclear fusion ignites. The thermonuclear fire stabilizes the star against further collapse, establishing stellar equilibrium, a balance between outward radiation and inward gravity. But even this stable phase is a momentary pause in entropy's broader flow. The star burns its fuel, gradually converting low-entropy hydrogen into higher-entropy helium and heavier elements. Over millions or billions of years, the star exhausts its reserves, and entropy continues its work. For smaller stars, the end is gentle, a transformation into white dwarfs, slowly cooling embers of the past. But for massive stars, the collapse resumes with brutal finality. Once fusion no longer provides sufficient outward pressure, the core succumbs to gravity. Within seconds, matter compresses to nuclear densities. The outer layers rebound violently, resulting in a supernova explosion, one of the most dramatic and energetic events in the universe. The core may become a neutron star, or if massive enough, collapse entirely into a black hole. It is in black holes that the connection between gravity and entropy reaches its most profound expression. Unlike any other object, a black hole's entropy is not proportional to its volume, but to the surface area of its event horizon. This revelation, first proposed by Jacob Bekenstein and further developed by Stephen Hawking, led to the stunning realization that black holes contain the maximum possible entropy for any given region of space. Hawking's work also showed that black holes emit radiation known as Hawking radiation due to quantum effects near the event horizon. This process, slow and imperceptible for large black holes, gradually converts mass into radiation, further increasing entropy as the black hole evaporates. Thus, gravitational collapse, far from being a negation of entropy, is one of its most powerful engines. It allows systems to transition from uniformity to structure in a way that increases total disorder in the universe. The apparent paradox, order emerging from disorder, is resolved when viewed through the lens of gravitational thermodynamics. Stars, galaxies, and black holes are not exceptions to the second law. They are its manifestations in curved space-time. This interplay is visible not just in individual stars, but across galactic scales. Galaxy clusters form through gravitational attraction, merging into larger and more complex systems As galaxies collide, their stars often pass through each other, but their gas clouds interact violently, triggering bursts of star formation. Meanwhile, dark matter halos shape the gravitational landscape, influencing how visible matter coalesces and moves. These structures embody high entropy in gravitational terms, even as they produce astonishing complexity and diversity. On smaller scales, gravitational collapse also plays a role in planetary formation. Within the disks of dust and gas orbiting young stars, particles stick together, clump, and accrete into planetesimals. These grow through collisions and gravitational attraction, eventually forming full-fledged planets. Though these processes produce coherent bodies, they involve the release of heat and radiation, contributing to the universe's overall entropy. The emergence of planets from chaotic disks is not a violation of thermodynamics, but its consequence. Even beyond the formation of structures, gravitational collapse is intimately tied to time's progression. As entropy increases through the redistribution of mass and energy, the arrow of time asserts itself. Galaxies age, stars evolve. Collapse proceeds. Entropy is not a passive observer in this drama. It is the clockwork behind every change. The reason these transformations are irreversible. A cloud that collapses into a star cannot spontaneously re-expand into diffuse gas. A black hole that forms from stellar death does not naturally unravel into its progenitor particles. Time, like entropy, flows one way. The dance of collapse and entropy also hints at deeper mysteries. In the field of quantum gravity, researchers are exploring how information and entropy relate in black hole interiors, how the geometry of space-time encodes thermodynamic data, and whether gravitational entropy is tied to the emergence of space and time themselves. Some theories suggest that space-time arises from entanglement and information flow, that the very fabric of reality is thermodynamic at its core. Gravitational collapse, then, is not merely an astronomical curiosity. It is a gateway to understanding how the universe builds and breaks, how entropy carves complexity, and how time itself gains direction. The entropic flow channeled by gravity gives rise to everything we know: stars that shine, worlds that turn, and minds that wonder. Yet these structures do not exist in isolation. In the crowded arenas of the cosmos, stars often gather in communities, clusters, bound by gravity, evolving together, exchanging energy and momentum. These star clusters are thermodynamic systems in their own right, revealing equilibrium not through isolation, but through dynamic interaction. On the other hand, as we move deeper into this unfolding narrative, we turn now to these celestial collectives and explore how dynamic equilibrium governs their fate in the entropic universe. Star clusters and dynamic equilibrium. In the long march of entropy, amid the gravitational collapses and thermodynamic transformations that define cosmic evolution, star clusters stand out as brilliant, tightly woven collectives. These celestial communities are not merely aggregations of stars, but finely tuned systems governed by the continuous balancing act between gravitational attraction, kinetic motion, and the thermodynamic laws that shape all matter and energy. In their flickering cores and sweeping halos, star clusters offer a compelling portrait of dynamic equilibrium, a state of ceaseless motion that nonetheless maintains overall stability. These clusters reveal that equilibrium in the universe is not always about stillness. Often it is about finely managed chaos. A star cluster is born from the collapse of a dense region within a molecular cloud, one rich in hydrogen and dust. As gravitational forces draw the cloud inward, fragmentation occurs, forming numerous protostars in close proximity. These newborn stars, still shrouded in gas and spinning rapidly, emerge together in compact regions, often spanning just a few light years. Unlike isolated stars, those in clusters begin life surrounded by siblings, bound not just by proximity, but by shared momentum and gravitational pull. This early stage is a chaotic environment, where mutual interactions are frequent and profound. Yet, even in this apparent disorder, the laws of physics enforce a form of equilibrium. There are two major categories of star clusters: open clusters and globular clusters. Open clusters are relatively young, loosely bound, and typically found in the spiral arms of galaxies. Their stars are fewer in number, ranging from a few dozen to several thousand, and often move apart over time due to internal dynamics or external gravitational perturbations. Globular clusters, in contrast, are ancient relics of galactic history. These massive spheres contain hundreds of thousands to millions of stars, densely packed in a spherical distribution that orbits the galactic core. Despite their age, these clusters persist due to the powerful gravitational bonds among their members and the thermodynamic equilibrium they collectively maintain. The key to understanding the equilibrium of star clusters lies in the principle of virial equilibrium, a concept central to astrophysical thermodynamics. The virial theorem, first formulated in the 19th century by Rudolf Clausius and later expanded for astrophysical systems, relates the kinetic energy of a system to its gravitational potential energy. In a stable, bound cluster, the average kinetic energy of the stars, how fast they move through space, is proportional to half the magnitude of their collective gravitational binding energy. If the kinetic energy becomes too high, stars will escape, and the cluster will evaporate. If too low, the cluster will collapse inward. True virial equilibrium occurs when these energies are balanced, allowing the cluster to remain stable over long periods. This balance is dynamic, not static. Stars within clusters constantly interact. Their orbits shift due to gravitational encounters, sometimes dramatically. Close encounters can transfer momentum, causing some stars to speed up and others to slow down. Over time, this leads to energy redistribution, known as relaxation. In smaller open clusters, this process proceeds relatively quickly, causing the cluster to dissolve as stars migrate away. In larger globular clusters, relaxation takes much longer, but it still plays a crucial role in shaping the system's structure and lifespan. Over time, heavier stars tend to migrate toward the center of the cluster, while lighter stars are flung toward the outskirts. This phenomenon, called mass segregation, arises naturally from energy exchange during stellar interactions. As a result, the core becomes increasingly dense, with more frequent collisions and binary formation. In some cases, these interactions lead to the creation of exotic objects like blue stragglers, anomalously hot and bright stars believed to form through mergers or mass transfer. The outer regions, meanwhile, slowly leak stars into interstellar space, gradually eroding the cluster. Star clusters are also subject to external influences. As they orbit within their host galaxies, they pass through spiral arms, encounter molecular clouds, or feel the tidal forces of the galactic core. These perturbations inject energy into the system, disturbing equilibrium and potentially accelerating the loss of stars. yet many clusters endure for billions of years, their dynamic equilibrium resilient in the face of external disruption. This persistence makes them valuable tracers of galactic history, preserving chemical and dynamical signatures of the environments in which they formed. Thermodynamically, clusters are fascinating laboratories. They are gravitationally bound systems that evolve slowly toward higher entropy, yet maintain internal structure and coherence. Their entropy increases through stellar evolution. Nuclear fusion within stars converts low-entropy hydrogen into higher-entropy helium and heavier elements. As massive stars die, they enrich the interstellar medium with heavy elements, contributing to galactic chemical evolution. White dwarfs, neutron stars, and black holes accumulate within the cluster, changing its gravitational profile and energy distribution. Each death, each merger, each escape contributes to the entropic tapestry. In some cases, clusters may undergo core collapse, a process where the central density increases dramatically due to runaway gravitational contraction. This can lead to the formation of intermediate mass black holes, or dense cores of compact remnants. The entropy of the cluster increases not through disorder alone, but through a transformation in its internal energy structure. At this stage, the concept of equilibrium becomes even more dynamic, governed by extremes, stabilized only by intense gravitational feedback. We have to act against a force that has been. Star clusters also connect thermodynamic theory with observable reality. Their structure, distribution, and stellar populations are studied through precise photometry and spectroscopy. Their color magnitude diagrams reveal their age, metallicity, and evolutionary state. Through these observations, astronomers infer not just the current state of a cluster, but its entire thermodynamic journey. These data, in turn, refine our understanding of entropy, equilibrium, and cosmic time. But star clusters are not just relics of the past, they are bridges to the future. They shape galactic evolution, seed planetary systems, and illuminate the pathways by which structure resists entropy's tide, at least for a time. And as they dissolve into the galactic halo, or spiral into the core, their stars become part of larger, more diffuse structures, continuing the flow of matter and energy through the universe. From the dynamic equilibrium of star clusters, our gaze turns now to another realm where entropy weaves its patterns. The swirling, blazing, ever-shifting environments of accretion disks, these luminous rings of gas and dust, spiraling around stars and black holes, are theaters of turbulence and transformation. It is within their incandescent spirals that gravitational energy is turned to heat, friction becomes radiation, and entropy takes center stage once more. Entropy in accretion disks. As the cosmic clock ticks forward, as entropy flows unrelentingly through galaxies and stellar clusters, there exists a special kind of engine, violent, luminous, and beautifully chaotic, where matter dances at the edge of annihilation. These engines are accretion disks, the swirling maelstroms of gas, dust, plasma, and debris that orbit compact objects such as newborn stars, neutron stars, and black holes. They're not static rings of material, but dynamic, turbulent systems where gravitational energy is converted into heat and light, where matter is transformed through friction and compression, and where entropy rises with terrifying efficiency. Accretion disks are born in gravitational collapse and maintained through angular momentum. When matter falls toward a massive object, it rarely descends in a straight line. Instead, due to its own angular momentum and the conservation laws that govern orbital motion, it spirals inward, flattening into a rotating disk. This geometry, thin yet wide, hot at the center and cooler at the edges, is the result of competing forces. Gravity pulling material inward, centrifugal force pushing it outward, and pressure and viscosity redistributing energy throughout the disk. It is in this tension that entropy flourishes. The fundamental thermodynamic nature of accretion disks lies in their energy conversion processes. As particles orbit closer to the center, they lose potential energy. But that energy does not simply vanish. Instead, it is transformed into heat through viscous interactions. Microscopic collisions, turbulence, magnetic fields, and shock waves all conspire to slow the rotation of matter and channel its gravitational energy into thermal energy. This heating drives temperatures in the inner regions of the disk to millions of degrees, causing the emission of high-energy radiation, including X-rays and ultraviolet light. These emissions are not passive byproducts, they are the visible footprints of entropy in motion, radiated proof of energy dissipation and rising disorder. Accretion disks are remarkably efficient at increasing entropy. Unlike stars, where fusion occurs only in dense cores, accretion disks radiate energy over vast regions. The inner edge of the disk, just outside the event horizon of a black hole or the surface of a neutron star, represents a zone of extreme thermodynamics. Here, matter is compressed, ionized, stripped of electrons, and spun at relativistic speeds. Friction and magnetic reconnection heat the plasma to such degrees that it can emit more light per unit mass than most stellar processes. The entropy produced in these inner regions is immense, calculated not merely as temperature or disorder, but as the total irreversible transformation of usable energy into radiation. In young stellar systems, accretion disks form around protostars, feeding them the mass necessary to initiate fusion. These protoplanetary disks also provide the material from which planets eventually form. Dust grains collide and stick, forming pebbles, rocks, and eventually planetesimals. As this process unfolds, entropy shapes the disk's evolution. Dust settles toward the midplane, ice lines, regions where volatile substances condense, determine where different planetary materials accumulate. As planets form, they carve gaps in the disk, redistribute mass, and alter temperature gradients. These changes in structure and composition reflect a shifting thermodynamic landscape, one where local order emerges even as global entropy increases. In high-energy astrophysics, accretion disks around black holes and neutron stars are laboratories for the most extreme conditions in the universe. In the case of stellar mass black holes or supermassive black holes in galactic centers, infalling matter emits powerful jets perpendicular to the disk plane. These relativistic jets, launched by magnetic fields twisted by the spinning disk, carry energy and momentum far into intergalactic space. Though the precise mechanism remains under investigation, the jets represent a way for accreting systems to balance angular momentum and energy, further illustrating the complex feedback loops between matter, gravity, and radiation. Yet even in these energetic displays, entropy continues to dictate the outcome. The disk converts organized orbital motion into randomized thermal energy. This heat escapes into space as radiation, irreversibly increasing the entropy of the surrounding environment. The inner disk regions, near the innermost stable circular orbit of a black hole, represent the thermodynamic frontier. Matter here reaches its final stages before crossing the event horizon, after which no information, no heat, no entropy can escape. The very act of crossing the horizon represents the ultimate entropic loss from the observable universe, locking energy behind a veil of space-time curvature. The thermodynamics of accretion disks also reveals itself through instabilities and transitions. These disks are not smooth, predictable structures. They are often unstable, fluctuating between quiet phases and outbursts. In systems like dwarf novae and X-ray binaries, sudden changes in disk viscosity or temperature can lead to dramatic increases in brightness. These outbursts are moments of rapid entropy production periods, where internal energy is suddenly released, heating matter and flooding the surrounding space with radiation. The thermal viscous instability model, for instance, explains how temperature-dependent opacity can cause runaway heating, disrupting equilibrium and creating cycles of eruption and recovery. Entropy in accretion disks does not rise monotonously. It surges, crashes and rebounds, much like weather patterns in planetary atmospheres or dynamic equilibrium in star clusters. This makes accretion disks excellent analogues for complex systems across physics. They are nonlinear, feedback-driven, and governed by local conditions, yet deeply shaped by global parameters such as mass, spin, and magnetic field. Studying them provides insight into broader thermodynamic questions: how order collapses into heat, how energy transforms irreversibly, and how structure can briefly persist within the relentless tide of entropy. In recent years, numerical simulations and high-resolution observations have allowed astrophysicists to peer into the heart of accretion disks with unprecedented clarity. Instruments like the Event Horizon Telescope have imaged the silhouette of black holes ringed by glowing material from accretion flows. These observations confirm theoretical models that predict extreme temperature gradients, frame-dragging effects from spinning black holes, and luminous emissions from rapidly inflowing gas. Every pixel in these images is a portrait of entropy at work, a snapshot of matter in its final moments, radiating energy into the cosmos before crossing a boundary from which nothing returns. From a cosmological perspective, accretion disks are not just exotic features. They are foundational engines of structure formation and energy redistribution. Supermassive black holes, fed by accretion, influence the evolution of entire galaxies. Their radiation can heat interstellar gas, regulate star formation, and alter galactic morphology. The entropy produced in these disks ripples outward, shaping environs millions of light-years across. Thus, the local entropy increase within a spinning ring of gas becomes a force of galactic change, extending entropy's reach to the largest known scales. And yet, these disks too must cool, must dissipate, must fade. Over time, as their fuel is consumed or ejected, they settle, their light dims, their thermodynamic journey reaches stasis. What remains is either a compact object, black hole, neutron star, or white dwarf, or a planetary system shaped by the fiery forge of accretion. In each case, entropy has done its work. It has transformed gravitational potential into radiant heat, structured matter into transient forms, and guided the irreversible flow of cosmic time. But the story does not end here. As galaxies swirl and evolve, and as stars consume their fuel, entropy continues to govern their formation and feedback processes. The next chapter in this grand thermodynamic odyssey turns to an even broader canvas. How entire galaxies, forming from primordial gas and evolving under feedback from stars and black holes, reflect the deeper principles of entropy, structure, and transformation. Galaxy formation is not simply a question of gravity. It is a thermodynamic drama written across billions of years, and it is to that unfolding narrative we now turn. Galaxy formation and thermodynamic feedback. As we journey deeper into the vast complexity of the universe, the narrative of entropy reveals ever more intricate expressions, no longer confined to isolated stars or accretion disks, but etched across entire galaxies. These colossal systems, composed of hundreds of billions of stars, rivers of gas, clouds of dust, dark matter halos, and supermassive black holes, are not mere gatherings of mass. They are living thermodynamic ecosystems. Galaxies form, evolve, collide, and age under the influence of gravity, radiation, chemistry, turbulence, and feedback processes that regulate the flow of energy and the transformation of matter. At the center of it all lies the same eternal principle: entropy, rising, expanding, directing. The formation of a galaxy begins in the primordial fog of the early universe, just hundreds of millions of years after the Big Bang. During this era, the universe had cooled enough to allow hydrogen and helium, the simplest and most abundant elements, to coalesce into vast clouds. These clouds were not uniformly distributed. Quantum fluctuations embedded in the fabric of space-time had seeded tiny overdensities. Under the persistent tug of gravity, these overdensities began to attract more mass, growing denser and hotter as they accumulated gas and dark matter. It is within these early gravitational wells that the first galactic structures began to form. Initially, these proto-galactic clouds were chaotic and dynamic. Gravity compressed gas toward the center, where temperatures soared due to adiabatic heating. As the gas collapsed, it shed angular momentum through collisions and turbulence, flattening into rotating disks. Primordial versions of spiral galaxies. Star formation began in bursts, triggered by compression and cooling. Supernovae, the explosive deaths of massive stars, quickly followed, injecting heat and heavy elements into the surrounding medium. These explosions not only enriched the environment with the ingredients for future stars and planets, but also stirred the gas, preventing it from collapsing too rapidly. This interplay between gravitational collapse and thermodynamic feedback defined the pace and structure of galactic evolution. This feedback loop between black holes and their host galaxies is one of the most extraordinary examples of self-regulating thermodynamic systems in nature. Despite operating on scales separated by many orders of magnitude, the mass of a central black hole correlates strongly with the velocity, dispersion, and total mass of its host galaxy's bulge. This empirical relationship suggests a kind of cosmic dialogue between gravity and entropy, a mutual shaping of mass, motion, and energy across scales that defies simple causality. The energy released by accretion regulates the thermodynamic state of the surrounding gas, which in turn governs the formation of stars and the growth of galactic structure. This energy-possessed monarch, and the hard lesson state is, galaxies themselves are not closed systems. They interact, merge, and collide in a ballet that stretches across billions of years. When two galaxies merge, their gas clouds compress, triggering starbursts, brief but intense periods of star formation. These bursts, in turn, lead to supernova feedback, AGN activity, and widespread heating. A thermodynamic consequence of a merger is profound. The distribution of entropy shifts. As cold gas is heated, angular momentum is redistributed, and dark matter halos blend. The resulting galaxy often stabilizes into an elliptical form, with older stars and less ongoing star formation. Over time, the entropy of such systems increases, not just in the thermodynamic sense, but in the information theoretic sense as well. Structure becomes more diffuse, less ordered, more randomized. In isolated environments, galaxies also evolve through internal processes. The gradual consumption of gas through star formation, combined with continuous feedback, leads to secular evolution. Spiral arms may wind tighter or become disrupted. Bars may form in central regions, redistributing mass and angular momentum. Over cosmic time, galaxies age. Their star-forming regions fade, and they become red and dead, filled with long-lived, low-mass stars that radiate weakly. This progression is an entropic one. Usable energy diminishes, disorder increases, and thermodynamic equilibrium is slowly approached. Prior to West, let us dear. What a bunch of absurd. Thermodynamic feedback, an umbrella term for processes that transfer energy from stars, black holes, or interstellar dynamics back into the galactic medium, is crucial to understanding how galaxies regulate themselves. Without it, star formation would proceed too efficiently, consuming gas at a rate inconsistent with observations. Feedback acts as a thermostat, injecting energy to maintain a delicate balance between cooling and heating. It helps prevent runaway collapse and sustains the equilibrium between structure and entropy. One of the most significant sources of feedback is the life cycle of massive stars. As they burn through their fuel, they emit powerful stellar winds, streams of charged particles that transfer momentum and heat into the surrounding gas. When they reach the end of their lives, these stars explode as supernovae, releasing vast quantities of energy. This energy heats the interstellar medium, increases local entropy, and disperses nearby clouds, sometimes halting star formation. At other times, the shock waves compress gas clouds, triggering new rounds of starbirth. This dual role, both destructive and creative, illustrates the complexity of feedback as a thermodynamic process. It does not push entropy in a single direction. It redistributes it, sculpting the internal architecture of a galaxy. Galactic feedback also operates on much larger and more violent scales. At the centers of most galaxies lie supermassive black holes, with masses millions or even billions of times greater than that of our Sun. When matter spirals into these black holes through accretion disks, it releases tremendous amounts of energy in active galaxies. Those where the central black hole is rapidly accreting, this process produces powerful jets, intense radiation and outflows that can heat or expel gas across vast distances. These active galactic nuclei, or AGN, inject entropy into the intergalactic medium, regulating the availability of cool gas and, by extension, the rate of star formation throughout the galaxy. Even in their aging, galaxies remain connected to the cosmic web, a vast network of filaments, voids and clusters shaped by gravity and dark matter. Gas flows along these filaments, feeding galaxies with fresh material or draining them of fuel. These flows represent entropic currents on the largest observable scales, transferring mass and energy from regions of lower entropy to higher entropy, always in line with the universe's relentless thermodynamic arrow. Galaxies thus serve as both products and engines of entropy. They emerge from low-entropy fluctuations, transform gravitational potential into heat and radiation, regulate themselves through feedback, and gradually dissipate their usable energy into the surrounding cosmos. Their beauty, the spiraling arms, glowing halos, thermobulges, is not just aesthetic, it is thermodynamic. It is the visible structure formed through the invisible logic of entropy. And yet, as galaxies evolve and thermodynamic feedback shapes their fate, they remain embedded in a deeper quantum fabric, a realm where entanglement, information, and the statistical behavior of particles further refine our understanding of entropy itself. As we pass from the macroscopic to the microscopic, from gravity-bound islands of stars to the non-local web of quantum connections, we must now ask how entropy behaves in this most mysterious of domains. What role does entanglement play in shaping entropy's rise? Can order and disorder coexist at the quantum level? In the next chapter, we descend into the strange and non-intuitive world of quantum entanglement, and how it challenges and enriches our understanding of thermodynamics across the universe. Quantum entanglement versus entropy. In the grand narrative of the cosmos, where gravity binds galaxies and stars burn through fusion, the laws of thermodynamics reign supreme. Entropy, the ever-rising tide of disorder, dictates the fate of all systems, from collapsing stars to expanding universes. Yet, beneath this classical reality lies a deeper, stranger substrate, a quantum world governed not by certainty, but by probability, not by objects, but by relationships. And within this quantum realm lies entanglement, a phenomenon so counterintuitive that even Einstein once called it spooky action at a distance. Entanglement defies locality, mocks classical separability, and rewrites the logic of information itself. When examined through the lens of entropy, entanglement reveals not only unexpected complexity, but profound insights into the very foundation of time, energy, and the fabric of space. At its core, quantum entanglement describes a situation in which two or more particles become so deeply correlated that the state of one cannot be fully described without reference to the other, no matter how far apart they are. Their wave functions, which describe probabilities rather than definitive states, intertwine. When a measurement is made on one particle, the state of its entangled partner is instantaneously affected. This is not because information travels faster than light, but because the two particles are no longer distinct in any conventional sense. They are aspects of a single quantum system. The correlations between entangled particles are stronger than any that can be explained by classical physics, and they have been repeatedly confirmed in experiments. But what does this quantum connectivity mean for entropy? Traditionally, entropy is a measure of disorder, or more precisely, the number of microstates compatible with a given macrostate. In classical thermodynamics, higher entropy implies greater randomness and less available energy. But in quantum mechanics, entropy is more closely linked to information. Quantum entropy, especially in the context of entanglement, measures the degree of ignorance one has about the parts of a system when only the whole is known. In other words, entanglement entropy quantifies how much two subsystems share information. Consider a pair of entangled photons. Together, they form a pure quantum state with zero entropy, completely known and fully coherent. Yet if you observe just one photon and disregard the other, the information becomes incomplete. The reduced state of one photon appears as a mixed state, with measurable entropy. This is not because the system is disordered, but because the act of separating the system for observation creates uncertainty. In this way, entanglement produces entropy not from randomness, but from correlation. It reveals a paradox. The more strongly two particles are entangled, the more information they lose individually. Their separability is an illusion, their individuality a construct of limited perspective. This insight leads to profound consequences for our understanding of thermalization, the process by which quantum systems approach equilibrium. In classical physics, thermalization is the result of particles colliding and exchanging energy until reaching a uniform temperature. In quantum systems, however, even isolated systems with no external interactions can evolve toward equilibrium-like behavior purely through entanglement. As different parts of a quantum system become entangled, the local subsystems appear to thermalize. The overall wave function remains coherent, but each part individually exhibits entropy, temperature, and irreversibility. This emergent behavior suggests that entropy may not arise from disorder at all, but from hidden order, an invisible web of correlations that mimic randomness through complexity. This quantum perspective also challenges our understanding of the arrow of time. If the fundamental laws of quantum mechanics are time-symmetric, meaning they work equally well forward or backward in time, then where does the irreversible flow of entropy come from? Some physicists propose that the arrow of time is not an intrinsic feature of reality, but a consequence of entanglement growth. As the universe evolves, quantum entanglement spreads. The degrees of freedom in the environment become increasingly intertwined with those of local systems. The observable world, seen through a limited lens, appears to drift toward higher entropy, even as the global wave function retains its time-reversible structure. Entropy, in this view, is a side effect of entanglement. This idea resonates strongly in the study of black holes, where entanglement and entropy converge in strange and powerful ways. According to the Bekenstein-Hawking formula, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This contradicts classical expectations and points to a deep connection between geometry, gravity, and information. The event horizon acts like a boundary of entanglement, a region where the degrees of freedom inside the black hole become inaccessible, entangled with the rest of the universe, but forever hidden. The entropy associated with this boundary encodes the information loss perceived by an external observer. Stephen Hawking's discovery that black holes emit radiation further complicates the picture. As a black hole evaporates, its mass and entropy decrease. But what happens to the information about the matter that fell into it? If that information is lost, as Hawking originally proposed, then quantum unitarity, the principle that information is preserved in quantum evolution, would be violated. This led to the famous black hole information paradox. Recent theories suggest that entanglement is the key to resolving this dilemma. Through processes involving quantum scrambling, wormholes, and holography, the entanglement between emitted particles may encode the hidden information, preserving unitarity even as entropy seemingly increases. Indeed, the notion that the universe may be a hologram, a three-dimensional reality projected from a two-dimensional surface, is rooted in entanglement entropy. The ADAS/CFT corresponders, a conjecture from string theory, suggests that gravity in a bulk space can be fully described by a quantum field theory on its boundary. In this duality, space-time itself emerges from entanglement. The geometry of the bulk corresponds to the pattern of entanglement in the boundary theory. Thus, space, time, and even gravity might not be fundamental entities, but emergent properties born from the entanglement of quantum bits. Entropy in this framework is not just a measure of disorder, it is the architecture of reality. Quantum entanglement also plays a growing role in quantum computing, where entangled qubits store and process information in ways impossible for classical systems. Entanglement allows quantum algorithms to explore multiple possibilities simultaneously, solving certain problems exponentially faster than any known classical algorithm. But managing entanglement also means managing entropy. Quantum deherence, the loss of entanglement due to environmental interactions, introduces noise and error. The battle between entanglement and entropy is not just theoretical, it is at the heart of the next generation of technology. Across these diverse realms, cosmic, computational, foundational, quantum entanglement reshapes our understanding of entropy. It reveals that disorder is not always random, that time's arrow may be woven from invisible threads of correlation, and that the very stage upon which the universe unfolds may be built from information itself. Entropy is no longer a blunt force driving systems toward equilibrium. It is an emergent feature of complex quantum relationships, a subtle fingerprint of entangled order masquerading as chaos. And as we trace this journey from quantum states to galactic evolution, we return again to the question of life. Amid this rising tide of entropy, life stands as a striking anomaly. A fleeting, local reversal, a pocket of decreasing entropy that persists and evolves. Can life itself be understood as a thermodynamic strategy, an entropic flow channeled through molecular complexity and information processing? In the next exploration, we will delve into this most astonishing phenomenon, how life, so improbable and fragile, emerges not in defiance of entropy, but because of it. Life as a local decrease in entropy. Through a journey spanning stars and galaxies, black holes and quantum entanglement, we have traced the silent thread of entropy as it guides the universe toward ever greater disorder. We've seen how galaxies regulate their structure through thermodynamic feedback, how black holes encode the entropy of entire regions of space within their event horizons, and how entanglement redefines our very understanding of time and information. And yet, amid this vast cosmic tide toward chaos and equilibrium, one phenomenon emerges that seems, at first glance, to defy the second law of thermodynamics. Life. Life is not exempt from entropy. It is built from it. But it channels entropy in such. To understand this, we begin with Earth, our only known cradle of life. Our planet is not a closed system. It receives a continuous influx of high-energy photons from the Sun. These photons arrive in concentrated, low-entropy forms, narrow wavelengths of visible and ultraviolet light. Earth absorbs this energy, uses it to drive chemical reactions, and then re-emits it back into space in the form of lower energy, higher entropy infrared radiation. The difference between the incoming and outgoing entropy enables the emergence of complex systems that harness energy, reduce local disorder, and build intricate patterns. Cells, organisms, ecosystems, and ultimately consciousness. Photosynthesis is the most direct example of this entropic alchemy. Green plants and cyanobacteria absorb sunlight and use its energy to assemble simple molecules like carbon dioxide and water into complex sugars. This is a decrease in chemical entropy, a transition from disordered, low-energy molecules into structured, energy-rich compounds. But it is not a violation of thermodynamics. The total entropy of the system, the plant, the sunlight, and the surrounding environment, increase. The plant becomes a node in a larger flow of energy, a processor that trades environmental disorder for internal complexity. The energy used to reduce its internal entropy is paid for by the radiation of heat into space. life evolves because it is thermodynamically favorable for certain molecular arrangements to persist, replicate, and adapt in response to external conditions. Thermodynamic principles. The fidelity of genetic replication, the error correction mechanisms of enzymes, and the complex regulation of gene expression are all methods of managing entropy. Mutation, while often harmful, is a statistical byproduct of entropic noise. Evolution rides this randomness, converting entropy into diversity, selection into adaptation. Ecosystems too are thermodynamic networks. They move energy from sunlight to plants, from plants to herbivores, from herbivores to predators, and finally to decomposers who return nutrients to the soil. Each step loses usable energy to heat, increases entropy, and yet supports local pockets of order. Biodiversity is an emergent property of entropy, channeled through structured relationships. The rainforest and the coral reef are no less products of thermodynamic flow than stars and galaxies, though their architectures are biological rather than astrophysical. As organisms increase in complexity, so too does their ability to process energy and information. Brains, the most energy-intensive organs in the animal kingdom, evolved as thermodynamic devices for making predictions. Neural networks reduce uncertainty, model environments, and generate adaptive behaviors. Human consciousness, the subjective experience of being aware, is the culmination of billions of years of entropic computation. It is an emergent property of energy and matter, arranged in highly improbable ways, a flickering spark of low entropy in a universe of increasing disorder. Our civilizations, technologies, and cultures are extensions of this process. They require immense flows of energy, vast systems of organization, and continual maintenance to persist. Cities, computers, language, science, all are examples of entropy temporarily redirected into forms of structure and information. But this order is always borrowed. It is sustained by consuming low-entropy resources and converting them into waste heat, pollution, and decay. The apparent defiance of entropy that life and civilization embody is made possible only by continually increasing entropy elsewhere. Yet life also shapes entropy. Through photosynthesis, Earth's atmosphere was transformed from a reducing to an oxidizing environment, enabling aerobic respiration and paving the way for complex life. Through geochemical cycling, biological activity regulates climate, ocean chemistry, and even plate tectonics. Life and planet are co-evolving thermodynamic systems, locked in feedback loops that span billions of years. The Gaia hypothesis, though controversial in its strongest forms, captures the essence of this interdependence. The biosphere is not separate from the Earth system, but an extension of it, optimizing entropy flows for continued habitability. In the broader cosmos, the thermodynamic uniqueness of life remains a mystery. Is Earth an anomaly, or is life a common result of entropy-driven processes? The search for biosignatures on exoplanets, the study of extremophiles on Earth, and the modeling of prebiotic chemistry all suggest that life could arise wherever conditions permit entropy to be locally reversed through external energy flows. If this is true, then life is not a rare exception, but a natural outcome, a thermodynamic solution to a planetary energy budget. As the universe ages and entropy continues to rise, the long-term fate of life becomes more precarious. Stars will burn out, galaxies will dim, black holes will evaporate, the free energy that sustains biological complexity will dwindle. In the far future, life, if it survives, may be reduced to computational patterns operating near absolute zero, harvesting the last scraps of usable energy in a universe slipping toward thermal equilibrium. The local decrease in entropy that defines life may one day vanish entirely, subsumed by the grand trajectory toward heat death. In the vast, ever-expanding frontier of human exploration, there exists a journey so awe-inspiring and monumental that it transcends the very boundaries of time and space. This epic voyage is none other than the extraordinary odyssey of Voyager 1, a pioneering spacecraft launched by NASA that has traveled farther than any other human-made object, carrying the hopes and dreams of humanity into the deepest reaches of the cosmos. Recently, Voyager 1 sent back a historic transmission to Earth that has ignited waves of excitement and curiosity throughout the global scientific community and beyond. At the heart of this remarkable message lies a discovery of unparalleled significance, an enigmatic object detected in the profound, uncharted depths of interstellar space. This mysterious revelation has reignited one of the most timeless and compelling questions that has captivated humanity for generations. Could this signal represent the long-awaited moment when we finally establish contact with advanced extraterrestrial life? For centuries, humankind has gazed up at the night sky with wonder, imagining the possibility of other civilizations thriving among the stars. Now, this revelation has brought those age-old dreams tantalizingly close to reality. Voyager 1's journey began decades ago when it was launched on September 5, 1977, as part of NASA's ambitious Voyager program. Its mission was bold and profound: to act as Earth's emissary, venturing beyond the familiar realms of our solar system into the vast unknown, while meticulously studying the outer planets and their moons. Voyager 1's remarkable voyage was marked by a serendipitous cosmic alignment. It set off just 16 days before its twin, Voyager 2, beginning a cosmic ballet that has unfolded for more than 40 years. What truly sets Voyager 1 apart from countless other space missions is its extraordinary spirit of communication. Despite its unfathomable distance from Earth, Voyager 1 maintains a steadfast dialogue with our home planet through NASA's venerable Deep Space Network. This complex and powerful communication system allows Voyager 1 not only to receive commands, but also to transmit back invaluable streams of scientific data, bringing us ever closer to understanding the cosmos. As of the latest measurements, Voyager 1 is an astonishing 159.32 astronomical units AU away from Earth, equivalent to nearly 23.8 billion kilometers, or approximately 14.8 billion miles. This staggering distance makes it the most distant human-made object ever to voyage into space. Yet, despite this incredible remoteness, Voyager 1's instruments continue to operate, tirelessly collecting and sending back information that deepens our understanding of the universe around us. Voyager 1's primary mission was to explore the outer boundaries of the heliosphere, the vast bubble of charged particles and magnetic fields generated by the Sun. This outer boundary, called the heliopause, marks the frontier where the influence of our star gives way to the cosmic environment of interstellar space. Crossing this threshold in 2012, Voyager 1 became the first human-made object to enter the space between stars, beginning a new chapter in space exploration. What makes Voyager 1's mission truly remarkable is not only its groundbreaking discoveries, but also its extraordinary endurance. Originally designed to last only a few years, Voyager 1 has surpassed all expectations, continuing its interstellar journey for over 4 decades. Each day, it cruises through the void at an incredible speed of approximately 38,000 miles per hour, sending precious data back to Earth across billions of miles. Scientists anticipate that Voyager 1 will continue this historic mission at least until 2025, when its power sources are expected to diminish. Equipped with a sophisticated suite of 10 scientific instruments, including cameras, infrared and ultraviolet sensors, magnetometers, plasma detectors, cosmic ray sensors, and radio science equipment, Voyager 1 was built to be humanity's eyes and ears in the cosmos. These instruments have enabled the spacecraft to withstand the harsh and unforgiving conditions of deep space, while delivering an unprecedented wealth of knowledge about the outer solar system and beyond. Among Voyager 1's most celebrated achievements are its close flybys of two colossal gas giants, Jupiter and Saturn. In 1979, Voyager 1 made its first close approach to Jupiter, revealing breathtaking details about the planet's turbulent atmosphere, intricate ring system, and diverse moons. The spacecraft's instruments confirmed the existence of faint rings around Jupiter, previously only theorized, and uncovered previously unknown moons that added to our understanding of the planet's complex environment. A year later, in 1980, Voyager 1's encounter with Saturn provided equally stunning insights. It unveiled the intricate structure of Saturn's iconic rings, captured detailed images of its moons, and deepened our knowledge of the planet's magnetic field and atmosphere. These flybys not only revolutionized planetary science, but also inspired a new generation of explorers, scientists, and dreamers around the world. One of the most iconic moments in Voyager 1's journey came in 1990, when the spacecraft, prompted by the visionary astronomer Carl Sagan, turned its cameras back toward Earth and captured the now famous image known as the pale blue dot. In this extraordinary photograph, Earth appears as a tiny speck suspended in a vast cosmic ocean, a fragile and precious home floating in the immense void of space. This image remains a powerful symbol of humanity's shared vulnerability and interconnectedness, reminding us of the urgent need to cherish and protect our only home. As Voyager 1 continues its silent journey through the darkness beyond our solar system, it carries with it the legacy of human curiosity, ingenuity, and the unquenchable desire to explore. Its latest discovery in the depths of interstellar space hints at new cosmic mysteries waiting to be unveiled, perhaps even the momentous encounter with other life forms that so many have dreamed about. This odyssey, which began over 4 decades ago, continues to inspire and challenge us, inviting us all to look up, wonder, and reach ever further into the vast expanse of the universe. Voyager 1 was designed to push the boundaries of human knowledge, traversing vast distances where no spacecraft had dared to go before. Equipped with a suite of sophisticated scientific instruments, it was tasked with studying the giant planets and their moons, capturing unprecedented data that would forever change our understanding of the solar system. What makes Voyager 1 truly extraordinary is not just its groundbreaking discoveries, but its resilience and longevity. Despite being launched over 4 decades ago, it continues to send invaluable information back to Earth, maintaining a lifeline of communication through NASA's Deep Space Network. This unwavering connection allows scientists to receive data from more than 14 billion miles away, a testament to human ingenuity and determination. As Voyager 1 journeys beyond the heliosphere, the protective bubble created by the Sun's solar wind, it enters interstellar space, a vast expanse filled with cosmic mysteries. Recently, a signal from Voyager 1 revealed the detection of an enigmatic object lurking in this farthest frontier. This revelation has sent shockwaves through the scientific community and reignited a question that has fascinated humanity for generations. Are we alone in the universe? The possibility that this mysterious detection could be evidence of advanced extraterrestrial life has captivated imaginations worldwide, inspiring scientists, philosophers, and dreamers alike to ponder the cosmic significance of this discovery. As we delve deeper into Voyager 1's findings, we are reminded of the boundless curiosity that drives human exploration, our relentless quest to understand not only the universe, but our place within it. In this unfolding cosmic saga, Voyager 1 stands as a symbol of hope, perseverance, and the unquenchable thirst for knowledge. Its voyage is not merely a scientific endeavor, but a profound journey that connects us all, uniting humanity in awe of the infinite cosmos that stretches beyond our wildest dreams. An intriguing aspect of the Voyager mission narrative lies in the remarkable timing. Voyager 1 began its epic journey just 16 days ahead of its cosmic twin, Voyager 2. This serendipitous alignment lends a sense of cosmic symmetry to an unparalleled saga. Two intrepid emissaries of humanity, launched in close succession, each destined to explore the uncharted realms of our solar system and beyond. What truly distinguishes Voyager 1 from countless other space missions is its indomitable spirit of communication, a lifeline that it maintains steadfastly with Earth across unimaginable distances. This extraordinary feat is made possible by NASA's venerable Deep Space Network, a robust and sophisticated communication infrastructure designed to ensure a constant dialogue between the spacecraft and its home planet. This unyielding link serves a dual purpose. It allows Voyager 1 to receive precise commands from mission control and, in return, to transmit a treasure trove of invaluable scientific data back to its terrestrial origins. According to the most recent data, Voyager 1 currently finds itself at an astonishing distance of approximately 159.32 astronomical units, AU, from Earth. To put this monumental achievement into perspective, this distance translates to an awe-inspiring 23.834 billion kilometers, or roughly 14.8 billion miles, away from the cradle of humanity. In other words, Voyager 1 is now the most distant human-made object in existence, a lone traveler venturing farther into the cosmic ocean than any other craft before it. This staggering remoteness not only speaks to the spacecraft's incredible durability and the brilliance of human engineering, but also marks a milestone in our quest to understand the universe around us. It is this incomprehensible remoteness that firmly establishes Voyager 1 as the most distant human-made object ever to embark on an odyssey into the vast cosmos. From the moment of its launch, Voyager 1's primary mission objective was clear and profoundly ambitious: to explore and meticulously scrutinize the boundaries of the outer heliosphere, a mysterious and barely understood region known as the heliopause. This invisible boundary marks the outermost layer of the Sun's influence, the final frontier where the solar wind meets the vast interstellar medium, enveloping our entire solar system in a protective bubble. Through its relentless investigations, Voyager 1 has bestowed humanity with invaluable insights into the cosmos, especially within the confines of our immediate solar neighborhood. Propelled forward at an astonishing velocity of approximately 38,000 miles per hour, an incredible speed that allows it to traverse vast cosmic expanses day by day, the spacecraft continues to push the boundaries of exploration and knowledge. Yet, What truly sets Voyager 1 apart is not just its distance or speed, but its remarkable endurance. The spacecraft has not merely met expectations, it has far exceeded its originally projected lifespan. More than 4 decades after its historic launch, Voyager 1 remains operational, tirelessly sending back vital data from the farthest reaches of space. Its ongoing mission serves as a testament to human ingenuity, perseverance, and an insatiable desire to understand the universe around us. Voyager 1 has embarked on extraordinary decades of exploration, defying the limits of time and technology. Each passing day, this remarkable spacecraft dutifully records and transmits vital information about its celestial journey, offering humanity a continuous stream of priceless data from the edge of our solar system and beyond. Remarkably, Voyager 1 is expected to continue this awe-inspiring interstellar sojourn until at least the year 2025, a testament to its resilient propulsion systems and enduring power supply that have kept it operational far beyond initial expectations. By that time, it is estimated that Voyager 1 will have achieved an almost inconceivable distance of approximately 13.8 billion miles from the nurturing embrace of the Sun, a staggering measure of its pioneering voyage into the cosmic unknown. Accompanying Voyager 1 on this grand adventure is its celestial sibling, Voyager 2, both launched as part of NASA's legendary Voyager program. Together, they were equipped with a formidable array of 10 unique scientific instruments, each serving as sensory extensions of the spacecraft into the vast cosmos. This sophisticated ensemble of tools included television cameras, infrared and ultraviolet sensors, magnetometers, plasma detectors, cosmic ray and charged particle sensors, as well as state-of-the-art radio equipment, all meticulously designed to conduct groundbreaking experiments. These ingenious instruments have endowed Voyager 1 with the resilience and capability to withstand the harsh and unforgiving environs of deep space, allowing it to probe the unfathomable reaches of the unknown. One of the most indelible milestones in Voyager 1's storied journey was its close encounters with 2 of the most majestic and enigmatic bodies in our solar system, Jupiter and Saturn. These historic flybys provided humanity with an unprecedented window into the complexities and wonders of these gas giants, forever reshaping our understanding of the planetary giants and their moons. Voyager 1's encounters with the solar system's colossal planets, Jupiter and Saturn, were nothing short of historic. These celestial rendezvous, which occurred in 1979 and 1980, respectively, marked a watershed moment in the annals of scientific discovery. Through these close flybys, Voyager 1 gifted humanity with an unprecedented glimpse into the intricate complexities of these gas giants and their enigmatic retinues of moons. The spacecraft etched its name indelibly into history by uncovering previously unknown moons orbiting these planets, and by revealing the intricate and delicate ring structures that encircled both Jupiter and Saturn. Prior to Voyager 1's mission, much of this was speculation or incomplete knowledge. Its groundbreaking revelations not only captivated the scientific community, but also ignited the imaginations of people across the globe, heralding a new era of planetary exploration. One of Voyager 1's most iconic and enduring contributions to our cosmic understanding came in 1990 when the celebrated astronomer Carl Sagan championed a visionary concept. He urged the spacecraft to pivot its cameras and direct its lens back towards Earth. This simple yet profound act resulted in the creation of the now famous image known as the pale blue dot. The resulting image, now deeply etched into the collective consciousness of humanity, depicts Earth as a minuscule pale blue dot suspended in the vast cosmic ocean. This poignant image serves as a humbling reminder of the fragility and interconnectedness of our planet, underscoring the imperative to cherish and protect our world. A message that continues to resonate powerfully with people around the globe. Voyager 1's epic journey through the cosmos led it to encounter two of the most enigmatic and majestic celestial bodies in our solar system, Jupiter and Saturn. These monumental encounters provided a treasure trove of scientific data and imagery, fundamentally reshaping our understanding of these gas giants. Jupiter, the largest planet in our solar system, beckoned Voyager 1 with its beguiling mysteries. In March 1979, the spacecraft conducted a close flyby of this colossal giant, granting humanity its first intimate glimpse of the planet's immense scale and complexity. As Voyager 1 ventured closer, it unveiled a tapestry of astounding discoveries. One of the most captivating being the confirmation of Jupiter's intricate ring system. Before Voyager 1's arrival, these faint rings were only a hypothesis, but the spacecraft's keen instruments provided definitive evidence of their existence. Composed of fine, dark particles, these delicate rings encircle Jupiter in an ethereal fashion. The images captured by Voyager 1 offered an entrancing perspective on this subtle feature, captivating the world with their delicate beauty and adding a new dimension to our cosmic knowledge. Another remarkable revelation from Voyager 1's encounter with Jupiter was the unveiling of intricate weather patterns and tempestuous storms on the gas giant's surface. Among these tempests, the most iconic was the Great Red Spot, a colossal storm that has raged for centuries. Voyager 1's imagery of this mammoth tempest not only illuminated the storm's complex structure and dynamic behavior, but also ignited the public's fascination with Jupiter's tumultuous atmosphere. Furthermore, Voyager 1's instruments detected Jupiter's powerful magnetosphere, a colossal magnetic field that dwarfs Earth's own magnetic envelope. This groundbreaking discovery provided crucial insights into the planet's magnetic dynamo and shed light on how this immense magnetic field interacts with its retinue of moons, influencing their environments and contributing to the complex space weather around Jupiter. Following its momentous encounter with Jupiter, Voyager 1 continued its epic odyssey toward Saturn, the majestic ringed planet. In November 1980, the spacecraft made its closest approach to this cosmic wonder, offering humanity an intimate view of Saturn's stunning rings and captivating moons. The detailed images and data collected unveiled previously unseen features of the ring's delicate structure and composition, as well as the diverse geology and atmospheres of Saturn's many moons. One of Voyager 1's most iconic contributions to human perspective came in 1990 with the celebrated pale blue dot image. The esteemed astronomer Carl Sagan championed a visionary idea. He implored the spacecraft to pivot its cameras and turn its lens back toward Earth. This image immortalized our planet as a tiny, fragile speck suspended in the vastness of space, inspiring reflection on our place in the cosmos and a renewed commitment to safeguarding our shared home. The resulting image, now etched deeply into the collective consciousness of humanity, depicts Earth as a minuscule pale blue dot suspended in the vast cosmic ocean. This poignant and humbling image serves as a powerful reminder of the fragility, vulnerability, and profound interconnectedness of our planet within the boundless expanse of the universe. It underscores the urgent imperative to cherish, protect, and preserve our delicate home, a message that continues to resonate with people from all corners of the globe, inspiring reflection on our shared responsibility to safeguard life on Earth. While Voyager 1's extraordinary odyssey primarily focused on the majestic gas giants Jupiter and Saturn, its twin spacecraft, Voyager 2, embarked on a distinct and equally remarkable trajectory. Voyager 2 was destined to explore the enigmatic ice giants of our solar system, Uranus and Neptune, planets shrouded in mystery and complexity, presenting a fresh array of cosmic enigmas for scientists and humanity to unravel. Uranus, the seventh planet from the Sun, is a celestial enigma for many reasons, not least of which is its extraordinary rotation. Unlike any other planet in our solar system, Uranus rotates on its side, with an axial tilt of approximately 98 degrees. This unusual orientation is believed to be the aftermath of a colossal and cataclysmic collision with a massive celestial object in the distant past, which drastically altered the planet's spin. This tilt results in extreme seasonal variations lasting over decades, offering a unique glimpse into planetary dynamics that differ greatly from those of Earth and its planetary neighbors. Despite its unusual tilt and mysterious origins, Uranus remains a captivating and fascinating world. It is approximately 4 times the diameter of Earth and boasts a cold, icy atmosphere composed mainly of hydrogen, helium, and methane, giving it a characteristic blue-green hue. Voyager 2's historic flyby of Uranus in January 1986 marked a momentous milestone in space exploration. For the first time, humanity received detailed images and comprehensive scientific data of this distant ice giant, expanding our knowledge far beyond previous telescopic observations. Among the many groundbreaking discoveries during Voyager 2's encounter was the revelation that Uranus possesses a complex system of rings, a surprising finding since rings were once thought to be unique to Saturn. Voyager 2 revealed that these rings consist of dark, narrow bands composed of tiny particles and debris orbiting the planet, hinting at dynamic processes within Uranus's gravitational influence. In addition to its rings, Voyager 2 discovered 10 new moons orbiting Uranus, each with its own unique characteristics and geological histories. The spacecraft's instruments also provided valuable insights into the planet's atmosphere, uncovering high-speed winds and unexpected temperature variations that challenged existing models of planetary atmospheres. These findings offered a new window into the workings of ice giants, enriching our understanding of planetary formation and behavior in the outer solar system. Voyager 2's journey did not end with Uranus. It continued onward to Neptune, the outermost planet in our solar system, arriving in August 1989. Neptune, with its striking deep blue color and fierce weather systems, presented yet another frontier of exploration and discovery. The data and images sent back by Voyager 2 from Neptune's vicinity revealed powerful storms, supersonic winds, and a moon with active geysers. An astounding discovery that further deepened our appreciation for the dynamic complexity of these distant worlds. Together, the twin Voyager spacecraft have revolutionized our understanding of the solar system's outer realms. Their pioneering missions, spanning more than 4 decades, have transformed once faint and distant dots in the night sky into vividly detailed worlds, full of mystery and wonder. These missions continue to inspire generations of scientists, dreamers, and explorers, reminding us that even at the very edges of human reach, the universe holds countless secrets waiting to be discovered. Voyager 2 revealed a diverse and captivating retinue of moons orbiting Uranus, each possessing unique geological and atmospheric features. Among these, moons like Miranda, Ariel, and Titania stood out, showcasing dramatic landscapes marked by massive canyons, unusual fault lines, and evidence of past geologic activity. These discoveries significantly enriched humanity's understanding of Uranus, shedding light on the complex interactions between the planet and its satellites, and deepening the intrigue surrounding this enigmatic, sideways rotating giant. Voyager 2's interstellar voyage did not end at Uranus. It pressed onward, journeying even farther to reach Neptune, the eighth and most distant known planet from the Sun. Neptune, with its frigid temperatures and vibrant azure hue, remains a haunting symbol of the solar system's outer frontier. This distinct blue coloration is due to the high concentration of methane in its atmosphere, which absorbs red light and reflects the blue. In August 1989, Voyager 2 conducted a historic flyby of Neptune, marking the first, and so far only, close encounter with this distant world. The images and data transmitted back to Earth during this flyby were nothing short of revolutionary. Voyager 2 unveiled a planet with a surprisingly dynamic atmosphere, teeming with violent storms and fierce winds, the fastest sustained winds recorded in the solar system, reaching speeds of over 2,000 kilometers per hour, about 1,200 miles per hour. Among Neptune's most notable atmospheric features was the discovery of the Great Dark Spot, a colossal storm system reminiscent of Jupiter's famous Great Red Spot. However, unlike its Jovian counterpart, the Great Dark Spot proved to be ephemeral. It mysteriously vanished in later observations, raising questions about the atmospheric dynamics of Neptune and the transient nature of its weather system. Perhaps one of the most astonishing revelations from Voyager 2's Neptune encounter was the discovery of the planet's largest moon, Triton, to be an exceptional celestial body that defied expectations. Triton orbits Neptune in a retrograde direction, meaning it moves in the opposite direction of Neptune's rotation, a rare trait that strongly suggests Triton is a captured object, possibly a former Kuiper Belt object that was gravitationally ensnared by Neptune in the distant past. Triton's surface was revealed to be a frozen yet geologically active world, exhibiting nitrogen geysers erupting from beneath its icy crust, a phenomenon never before observed on a celestial body so distant from the Sun. This cryovolcanic activity indicated that Triton, despite its remoteness and frigid temperatures, harbors internal heat and dynamic processes beneath its surface. Voyager 2's images showed a landscape marked by frozen plains, ridges, and sparsely cratered terrain, suggesting a young and possibly evolving surface. These groundbreaking discoveries at Neptune and Triton not only captivated the global scientific community, but also sparked the imaginations of people around the world. The Voyager 2 mission demonstrated the boundless potential of human curiosity and ingenuity, reminding us that even the most remote and mysterious corners of our solar system can be brought into the realm of human understanding. Voyager 2's historic flybys of Uranus and Neptune marked the end of humanity's first grand tour of the outer planets, a monumental chapter in the annals of space exploration. Yet, like its twin Voyager 1, Voyager 2 continues to voyage beyond the known, transmitting faint whispers of data from the edge of interstellar space, ensuring that its legacy endures not just in scientific discovery, but in the shared human spirit of exploration. Triton, the largest moon of Neptune, emerged as one of the most fascinating and enigmatic celestial bodies encountered during Voyager 2's interplanetary odyssey. The spacecraft's imagery revealed a world brimming with activity, despite its remote location and frigid climate. Among Triton's most extraordinary features were geysers that erupted from beneath its icy surface, spewing nitrogen gas high into the Moon's thin atmosphere. These geysers created vast plumes that extended kilometers above the surface, where the nitrogen would condense into snow-like particles and gently settle back to the ground, sculpting a surreal and alien landscape of frost and ice. This striking phenomenon was unlike anything previously observed in the solar system, offering profound insights into cryovolcanism, the eruption of volatile substances like water, ammonia, or methane, rather than molten rock. Triton's surface, relatively young and sparsely cratered, hinted at a geologically active history, defying expectations for a moon so far from the Sun. Perhaps even more puzzling was Triton's retrograde orbit. It revolves around Neptune in the direction opposite to the planet's rotation. This uncommon trait strongly suggests that Triton did not form alongside Neptune, but was instead a captured object, likely originating from the Kuiper Belt. Its gravitational capture would have disrupted Neptune's original satellite system and left Triton locked in a stable but unusual orbital dance, one that continues to intrigue astronomers to this day. Voyager 2's encounters with Uranus and Neptune remain unparalleled achievements in the history of space exploration. To this day, no other spacecraft has visited these distant ice giants, making Voyager 2's observations and data collection an irreplaceable scientific treasure. The trove of information gathered during these historic flybys continues to fuel research and hypotheses, offering glimpses into the atmospheric dynamics, magnetic fields, ring systems, and unique satellite compositions of these mysterious worlds. While Voyager 2 was delving into the secrets of the outer planets, its twin, Voyager 1, was forging an even more audacious path, a journey that would take it beyond the boundaries of the solar system and into interstellar space. This transition, which occurred in August 2012, marked a profound and historic milestone for humanity. For the first time, a human-made object had crossed the heliopause, the boundary where the solar wind yields to the interstellar medium. Voyager 1's entry into interstellar space did not signify the end of its mission, but rather the beginning of a new chapter. As it continues its voyage through the vast and silent reaches of the cosmos, it carries with it not only scientific instruments, but also a symbolic message from Earth, etched in the form of the Golden Record, a phonograph disc containing sounds, music, and greetings from our planet. Now billions of miles from Earth, Voyager 1 operates in a realm beyond the Sun's influence, where the environment is dominated by particles, fields, and forces that originate from other stars. Its instruments, though fewer in number now, continue to return invaluable data about the nature of interstellar space, helping scientists to understand the shape and boundary of the heliosphere and the conditions in the space between the stars. The enduring journey of the Voyager spacecraft, Voyager 1, venturing outward into the galaxy, and Voyager 2, providing the only close-up views of Uranus and Neptune, remains one of the most ambitious and successful missions in the history of space science. They have not only expanded the boundaries of human knowledge, but have also inspired generations to look upward and dream of what lies beyond, gathered groundbreaking data that challenged earlier assumptions and reshaped our understanding of this mysterious frontier. Rather than a simple comet-like structure with a long tail trailing away from the Sun, Voyager 1's measurements suggested that the heliopause is more complex, possibly a distorted bubble-like shape influenced by both the solar wind from within and interstellar forces from beyond. As Voyager 1 crossed this boundary in 2012, it recorded a sudden and lasting drop in solar particles, while simultaneously detecting a surge in galactic cosmic rays, energetic particles that originate from supernovae and other powerful cosmic phenomena far outside our solar system. This was the smoking gun, clear empirical evidence that the spacecraft had exited the heliosphere and entered the vast ocean of interstellar space. Within this realm, Voyager 1's instruments continued to function, albeit in a limited capacity due to the fading power supply and increasing distance. Even so, its plasma wave subsystem detected a persistent background hum, long, low-frequency vibrations in the plasma of interstellar space. This discovery provided an unprecedented glimpse into the density and behavior of particles between the stars, and demonstrated that the void of space is, in fact, filled with subtle and dynamic forces. Voyager 1's ongoing mission in interstellar space is a testament to both technological resilience and scientific ambition. It represents the first time humans have been able to directly measure the environment of interstellar space, rather than relying solely on telescopes or theoretical models. The data sent back by Voyager 1 continues to challenge assumptions and refine our models of how the Sun interacts with the galaxy around it. As it sails farther into the unknown, Voyager 1 is also pushing the limits of communication, its faint signals traveling at the speed of light now take over 22 hours to reach Earth. Each byte of data is a time capsule, whispering stories from the edge of the solar system to a waiting world. Despite being over 46 years old, the spacecraft continues to surprise. In recent years, engineers have performed innovative workarounds to keep it operational, including rerouting functions through backup systems. These efforts ensure that even in its twilight years, Voyager 1 remains a pioneer, a silent emissary of Earth, drifting among the stars. Its journey into interstellar space is not just a scientific achievement, but a symbolic one. Voyager 1 carries the golden record, a carefully curated message intended for any intelligent life that might one day encounter it. Engraved with greetings in 55 languages, music from cultures across the Earth, and images depicting life on our planet, the golden record serves as humanity's cosmic calling card, a whisper to the universe saying, "We were here, we reached this far, and we are curious." Voyager 1 is now far beyond the planets, beyond the influence of our star, continuing its voyage in the silence of deep space. It is alone, yet never forgotten. His legacy etched into history, its mission ongoing, and its story inspiring countless new explorers to reach for the stars. These observations from Voyager 1 provided a transformative understanding of the heliopause and its complex relationship with the galactic environment. Prior to Voyager's journey, much of what scientists knew about the heliosphere was theoretical, based on models, simulations, and indirect evidence. But as Voyager 1 approached and eventually crossed the heliopause, it delivered empirical measurements that revolutionized the field. One of the most unexpected discoveries was the behavior of the magnetic field at the boundary. Scientists had expected a sharp shift in the direction of the magnetic field lines as Voyager 1 transitioned from the Sun's influence to the interstellar medium. However, what they observed was a subtle and unexpected continuity. The magnetic field beyond the heliopods remained aligned in a way that puzzled researchers. This anomaly suggested that the heliosphere might not be as sharply defined or as neatly contained as once imagined. Instead, it could be intertwined or blended with interstellar forces in ways that challenge our understanding of the boundary between solar and galactic domains. These deviations hinted at previously unknown interactions between the solar wind and the interstellar magnetic field, painting a far more dynamic and fluid picture of the Sun's outermost frontier. In addition to its findings on magnetic fields, Voyager 1 also measured plasma density in interstellar space. Unlike within the solar system, where plasma is sparse and influenced by solar activity, the interstellar medium was found to be denser, yet cooler and more stable. This provided critical data that helped astronomers refine their understanding of the material that fills the vast regions between star systems. Voyager 1's traversal into and beyond the heliopause did more than just expand the scientific boundaries of astrophysics. It redefined the scale of our solar system. What was once thought to end at the orbit of Pluto, or perhaps Neptune, was now clearly shown to extend tens of billions of kilometers farther. Enveloped in a vast and shifting magnetic bubble, these findings are not merely academic. They have profound implications for future missions and our long-term aspirations for space travel. Understanding the heliosphere's structure is essential for developing technologies that could one day protect human explorers from cosmic radiation as we venture further from Earth. It also helps in mapping the interstellar environment that any spacecraft, robotic or crewed, would encounter as it journeys to the stars. In essence, Voyager 1's study of the heliosphere turned a once theoretical concept into a tangible and measurable structure, revealing it as a living, breathing force field that protects and defines the domain of our Sun. And while many questions remain about its shape, its interaction with the galaxy, and how it evolves over time, Voyager 1 laid the first real footprints on this invisible frontier. It's a testament to human curiosity and engineering that a spacecraft launched in 1977 continues to inform us decades later about regions of space we had never directly touched before. The mission of Voyager 1 not only broadened our understanding of the heliosphere, but also reminded us that exploration, no matter how distant or difficult, brings us closer to the truth of our place in the cosmos. These contrasting environments encountered by Voyager 1 and Voyager 2 as they crossed the heliopause added profound depth to our understanding of interstellar space. Although both spacecraft pierced the boundary that separates the Sun's protective bubble from the galaxy beyond, the variations in local space weather, magnetic field intensity, and particle density between their paths suggested that interstellar space is not uniform. It is a complex and evolving landscape, shaped by both local and galactic forces. Voyager 2's instruments, still fully operational at the time of its heliopause crossing, recorded direct plasma measurements, something Voyager 1 could not do initially due to a malfunction in its plasma instrument. This allowed Voyager 2 to directly confirm the dramatic rise in plasma density beyond the heliopause, complementing the data Voyager 1 had previously inferred using its cosmic ray and magnetic sensors. This corroboration between two different observational methods provided compelling evidence for a denser interstellar medium just outside our solar system. Moreover, the turbulence Voyager 2 encountered, manifested as fluctuating magnetic fields and wave-like plasma interactions, indicated a more chaotic boundary layer. Scientists hypothesize that this may be due to differences in solar wind pressure or local interstellar cloud structures that distort the heliosphere's edge. In contrast, Voyager 1's path appeared to be through a calmer, more sensitive this frontier is to cosmic condition. Together, these findings from both spacecraft are enabling scientists to create the first three-dimensional models of the heliosphere's outer boundary, which help illustrate its shape, behavior, and interaction with the galaxy. These models are crucial not only for understanding our own solar environment, but also for contextualizing the protective magnetic bubbles that might surround other stars, possibly shielding exoplanets from harmful radiation and influencing their potential to host life. In essence, Voyager 1 and Voyager 2, though launched within weeks of each other, have become dual ambassadors to the galaxy, each offering a distinctive lens on the final frontier of our solar system. Their separate experiences highlight that the edge of our solar system is not a fixed wall, but a living, breathing boundary, shaped by the solar wind's strength, the interstellar medium's density, and galactic magnetic fields that we are only beginning to understand. As Voyager 2 continues its journey through this turbulent interstellar zone, it adds more layers to the grand narrative begun by its twin. Together, they are charting a realm never before visited by humankind. And in doing so, they remind us that even at the edges of our influence, human curiosity and ingenuity still thrive. Reaching out into the unknown, guided by the faint whispers of data traveling billions of kilometers back to Earth, journey marks both a triumph of engineering and a poignant reminder of the finite nature of even our most enduring creations. Now well over 46 years since its launch, Voyager 1 continues to drift deeper into the uncharted sea of interstellar space, carrying with it the legacy of Earth's first true attempt to reach beyond the confines of the Sun's domain. Yet, as the spacecraft travels ever farther, it faces increasing challenges. Its power supply, generated by radioisotope thermoelectric generators, RTGs, is gradually weakening. As of now, NASA engineers have been shutting down non-essential systems to conserve energy and extend the mission's lifespan. Sometime in the late 2020s or early 2030s, Voyager 1 will likely go silent, as its power becomes insufficient to sustain even the low-energy communications that still reach Earth today. Despite this inevitable silence, the spacecraft will not stop traveling. Long after it can no longer send signals or power its instruments, Voyager 1 will continue coasting through the Milky Way galaxy, a silent sentinel bearing the golden record, waiting for a distant intelligence, if such an intelligence exists, to encounter it. This golden record, painstakingly curated by a team led by Carl Sagan, includes readings in 55 languages, music from a wide range of cultures and eras, from Bach and Beethoven to traditional songs from Japan, Senegal, and Peru. Images depicting life on Earth, human anatomy, architecture, DNA structures, and the planet's ecosystems. Sounds of Earth, including the laughter of a child, the roar of the ocean, thunder, and the chirping of birds. These records serve as a kind of cosmic message in a bottle, not with the hope of rescue, but as a declaration: we were here. We reached for the stars. We tried to understand the universe and ourselves. In this way, Voyager 1 and Voyager 2 have transcended their original scientific missions. They have become monuments of human creativity and persistence, testaments to a civilization that dared to send its voice into the dark with no guarantee of reply. They represent an act of faith in the future, a belief that knowledge, wonder, and the desire to explore are enduring parts of what it means to be human. As we gaze toward the heavens, tracking the faint signals from these emissaries, we are reminded that our reach has already extended beyond the solar system, and that even in the cold emptiness of space, our story continues. The Voyager mission teaches us that the journey itself, filled with discovery, wonder, and enduring hope, is as important as the destination. Voyager 1's incredible journey has reignited the world's fascination with this fearless spacecraft after more than 4 decades of exploration. Voyager 1 has traveled far beyond our solar system, venturing deep into interstellar space. It has crossed the heliopause, the boundary where the sun's influence fades, and now drifts through a vast, uncharted region of the galaxy. In August 2022, Voyager 1 sent a mysterious message back to Earth, one that captured the imagination of scientists and space fans everywhere. Amid streams of data and telemetry, researchers detected a strange anomaly, an object of unknown origin and makeup. Tentatively named the Cosmic Enigma, this object is unlike anything ever encountered in the history of space exploration. What makes the Cosmic Enigma so puzzling? It emits faint, irregular signals that don't match any known natural celestial phenomena. Even more intriguing, its path through space seems deliberate, as if it's following a specific course through the cosmos. This discovery raises deep and fascinating questions. Where did this object come from? Who or what created it? And what might its intentions be? Scientists and astronomers around the world have been meticulously analyzing the data sent by Voyager 1, determined to unlock the secrets of the mysterious cosmic enigma. Could this baffling object be a remnant of an advanced extraterrestrial civilization, or perhaps a probe launched from a distant corner of the galaxy? Alternatively, might it be an entirely new and unknown cosmic phenomenon? The discovery has ignited a wave of speculation and debate, bringing together experts from diverse fields who are collaborating to unravel the enigma's true nature. One leading theory suggests that the cosmic enigma could be an ancient relic from a long-lost civilization, a probe dispatched eons ago, its original mission veiled in the mists of time. Whether its purpose was scientific, exploratory, or something beyond our imagination remains an intriguing mystery. On the other hand, some scientists propose that this object might be a natural celestial phenomenon, with properties that challenge our current understanding of astrophysics. This possibility reminds us of the universe's immense complexity and the vast diversity of cosmic phenomena still waiting to be discovered. It highlights how much we have yet to learn and how little of the universe's secrets we have uncovered. The detection of the cosmic enigma underscores the critical importance of continued space exploration. It calls for humanity to push further into the cosmos, to embrace the unknown, and to expand our cosmic reach. The universe is a vast, mysterious frontier, filled with wonders and enigmas that inspire awe and curiosity. As Voyager 1 continues its solitary voyage through interstellar space, carrying with it the mystery of the cosmic enigma, humanity stands on the brink of new discovery. This spacecraft has become Earth's ambassador to the stars, a shining symbol of our insatiable curiosity and unyielding desire to explore. Voyager 1's odyssey, spanning over 4 decades, has fundamentally reshaped our understanding of the universe. It continues to inspire generations of scientists, dreamers, and stargazers alike. As we ponder the mysteries of the cosmic enigma and the endless possibilities it represents, we are reminded that the cosmos is a vast, wondrous, and ever-evolving realm. Each new discovery brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? With its indomitable spirit and enduring mission, Voyager 1 carries our hopes and dreams as it forges onward into the cosmic unknown. The story of Voyager 1 is a testament to the enduring human spirit of exploration, curiosity, and the relentless quest for knowledge. It transcends time and space, reminding us of our place in the universe and the boundless wonders awaiting us in the cosmic expanse. The Enigma of the Cosmic Enigma serves as a poignant reminder that the universe is filled with mysteries yet to be unraveled. It invites us to continue our cosmic journey with wonder and humility, ever eager to explore the depths of the unknown. Voyager 1, humanity's cosmic emissary, continues to inspire us to reach for the stars and embrace the infinite possibilities that lie beyond.